Before the beginning, before light and matter, even before time itself, there is only a void. It is a void not of darkness as we understand it, for even darkness implies the existence of space. Instead, imagine a state of nothingness beyond our comprehension. No up or down, no yesterday or tomorrow. An infinite stillness with no clock to tick. In this great emptiness, the seeds of everything lie dormant, waiting for a spark to ignite existence. This is the threshold of the unknowable, a realm beyond the dawn of time. For countless ages, philosophers and scientists alike have pondered what, if anything, came before the universe's beginning. Our story of the cosmos typically starts with a brilliant flash, the Big Bang, an event nearly 14 billion years ago when the observable universe blossomed from an unimaginably hot, dense state into the vast expanse we see today. At that moment, time and space as we know them were born. But our curiosity drives us further back to wonder, what was happening before that first moment? Can the concept of before even apply when time itself may not yet have existed? The truth is, we do not have a definitive answer. The equations of physics, as we understand them, break down as we approach the Big Bang's singularity, a point at which density and energy become infinitely large. All the matter and energy of the universe, compressed into an inconceivably small point, create conditions that our current theories cannot describe. In that primeval instant, less than a trillionth of a second from the start, our familiar notions of space and time lose their meaning. To truly grasp what happened at or before that moment, we would need a complete theory of quantum gravity, a unification of the very large and the very small, a theory that eludes us still. And so, we venture into the realm of educated imagination. There are many ideas, each fascinating, all unproven, about what preceded the birth of our universe. One idea posits that our universe is just one bubble in a frothing cosmic ocean of universes, a part of a grander multiverse. In this view, space on the largest scale is endlessly expanding and inflating, much like an ever-growing foam. Occasionally, in that inflating space, a tiny region might slow down and pinch off, budding into a distinct universe with its own Big Bang, just as ours did. If this is true, then before our Big Bang, there may have been another space or another universe that gave rise to our own. Our universe's birth would then be akin to a bubble forming within a vast cosmic sea, one of countless others destined to grow, perhaps spawn new universes of their own, or eventually fade. Another tantalizing idea is the concept of a cyclic universe, an eternal series of cosmic deaths and rebirths. Imagine the universe as a phoenix, periodically collapsing in on itself and then bursting forth anew. In such models, the Big Bang was not the absolute beginning, but rather the aftermath of a previous universe that ended in a kind of big crunch. Perhaps the universe expands for trillions of years. Then gravity slowly halts and reverses that expansion, pulling everything back into a single point again, only for that point to rebound in a new Big Bang, starting the cycle over. If this is the case, our current cosmos might carry subtle imprints of the universe that came before, and our distant descendants, trillions of years hence, might witness the next contraction and rebirth. It's a dramatic vision, a cosmos without a true beginning or end, but rather an infinite loop of creation. Then there is the profound notion that asking what came before the Big Bang might be as meaningless as asking what lies north of the North Pole. In the theory first hinted by Stephen Hawking and others, time itself could be finite and unbounded. They suggest that as we trace time backward to the very first moments of the Big Bang, time could gradually transition into something like a spatial dimension. In this scenario, the universe might have no sharp beginning at all, no singular moment where time starts with a bang, but instead a smooth, rounded origin, much like the South Pole of Earth is a point where all lines of longitude meet, yet there is no further south beyond it. The Big Bang would then be not a creation ex nihilo, but a transition in the state of the cosmos. Before that transition, time as we know it simply did not exist or had no meaning. Consider also the possibility of a vacuum fluctuation, a spontaneous emergence of the universe from nothing. In quantum physics, even a perfect vacuum seethes with tiny, fleeting particles blinking in and out of existence. Some theorists have imagined that our entire universe might have begun as just such a quantum event, a random fluctuation that through a quantum tunneling effect grew into the fireball of the Big Bang. From essentially nothing, no matter, no energy, not even space, a little bubble could appear, containing enormous energy borrowed from the vacuum itself, allowed by quantum uncertainty. Normally such a bubble would vanish as quickly as it appeared, but if conditions were just right, it might inflate rapidly and become stable, evolving into a full-fledged universe. It's a mind-bending idea that perhaps nothingness is inherently unstable, and given long enough, it inevitably spits out universes. These concepts stretch our imagination and strain our understanding of reality. They dwell at the edges of science, where evidence is scarce or indirect. We search the sky for clues. Subtle patterns in the cosmic microwave background radiation, the afterglow of the Big Bang, might hint at collisions with other universes, or reveal a cyclic imprint of events before our Big Bang. Thus far, no clear signals have emerged. The cosmic microwave background is like a foggy window beyond which we cannot see. It comes from a time about 380,000 years after the Big Bang, beyond which the universe was opaque. Anything before that time is veiled from our view by this hot mist of the early cosmos. And anything before the Big Bang is even further beyond our observational reach, perhaps forever. Yet, our minds persist in wondering. Picture that primordial epoch from which time emerged, an unfathomable stillness, perhaps punctuated by tiny quantum flickers. Then, a breakthrough, a surge of unimaginable brightness and energy as the Big Bang erupts into being. Time begins to tick. A chaotic, boiling plasma floods what will become space. In that incandescent moment, all the potential of stars, galaxies, and life itself is born. It is a moment we can describe in broad strokes, thanks to physics. We know that fractions of a second after the Big Bang, the universe inflated spectacularly fast, smoothing and expanding the tiny newborn cosmos. We know that as it expanded, it cooled, and energy began turning into particles. But the exact moment of creation, and anything that might precede or surround it, remains hidden behind a veil of mystery. We are like explorers, standing at the edge of a great ocean at night, aware that something lies beyond the horizon, but unable to sail further. We can only infer and imagine what shores might lie in the darkness. What set the universe in motion? Was it a quantum quiver in the void? The rhythmic heartbeat of a cyclic cosmos? Or an inscrutable event entirely outside the scope of our physical laws? Each possibility raises new questions. If ours is one bubble in a multiverse, what are those other universes like? Can they ever interact with ours? Or are they forever separate, like distant galaxies we'll never reach? If the universe is cyclic, what mechanism restarts it? And what was the first cycle? Or has it truly been cycling eternally, without any beginning at all? Even the language we use strains to describe these ideas. Before time. How can we conceive of a before without time? When we say outside our universe, what do we envision? An external space beyond space. Perhaps such terms are just shadows of understanding, placeholders, until we have better words, born from a deeper theory, to describe the reality of it. As we float in this contemplation, we should acknowledge that the mystery of the universe's origin is not just a question of physics, but also one that touches on philosophy and even metaphysics. Throughout history, many cultures and traditions have their own creation stories, attempts to explain how something can arise from nothing. Modern cosmology's scientific narrative is our latest attempt, grounded in mathematics and observation, yet it too reaches a hazy frontier where empirical evidence gives way to conjecture. One day, if we are fortunate, new physics might emerge to guide us further. Perhaps a breakthrough in quantum gravity theory will allow us to peer conceptually past the singularity. Maybe subtle evidence in high-energy particle experiments or astronomical observations will hint at pre-Big Bang physics, maybe in the form of gravitational waves from the very first instance of the universe that could carry an echo of what came before. Scientists have even proposed that tiny black holes created just after the Big Bang, if found, might carry information from those extreme times. For now, however, before the Big Bang remains one of the universe's greatest enigmas. It humbles us, reminding us that there are limits to our knowledge, at least for the moment. Here, at the dawn of time's horizon, we stand and gaze into the darkness that came before light, feeling the profound mystery wash over us. In this silence before creation, we sense the depths of our universe's secrets, an origin story that is still unwritten in the language of science. From this contemplation of the timeless void and the birth of everything, we gently turn our attention to the next great mystery. If the Big Bang set the stage and time began, the first act of our cosmic story raises another profound question. Once the universe existed, why was it filled with something rather than nothing at all? The mere existence of matter, of stars, planets, and ourselves, is not as straightforward as it seems. As the newborn universe expanded and cooled, it produced equal parts of matter and its mirror twin, antimatter. By all rights, these should have destroyed each other completely, leaving a barren cosmos without any matter. And yet, here we are. How did anything survive that initial cataclysm? It is to this riddle, the imbalance between matter and antimatter, that we now turn as we journey onward through the enigmas of deep space. In the fiery moments of creation, the universe was a hot cauldron of energy. As it expanded and cooled just a touch, that energy congealed into pairs of particles. One normal particle of matter and one particle of antimatter, locked in an intimate, lethal dance. Every particle that flashed into existence had a counterpart. The electron with its oppositely charged twin, the positron, the proton with the antiproton. Even neutrons had opposite versions. These antimatter particles mirrored ordinary matter in almost every way. Same mass, same spin, but with charges and certain properties reversed. And when matter met antimatter, they annihilated in a burst of pure light, returning their mass energy back to the searing glow of the young cosmos. In theory, the birth of the universe should have been perfectly symmetric. For every matter particle, an antimatter particle, equal and opposite. As the universe cooled further, those particles should have sought each other out and mutually obliterated, leaving nothing but a sea of photons, light, racing through an empty universe. If that had happened completely, no atoms, no stars, or planets would ever have formed. The cosmos would be a radiance without substance, a light without any source. It would truly be a universe of nothingness, despite all the energy. Yet, as we look around, we see that did not happen. There is something rather than nothing. We ourselves are here. Earth and all its living beings exist. The stars shine, and galaxies swirl in the darkness. The question is, why? What saved a fraction of matter from total annihilation? How did the scales tip ever so slightly to one side, favouring matter, allowing a material universe to take shape? Scientists believe that in those first fleeting instants, within the first second of creation, a tiny imbalance must have emerged. Out of perhaps 1 billion matter-antimatter pairs that formed and quickly annihilated, there might have been just one extra particle of matter that had no partner to destroy it. 1 in 1 billion survived, a lone seed of matter left over from a vast, furious cancelling out. It doesn't sound like much, but those 1 in 1 billion survivors accumulated. As the universe continued to expand and cool, the continual creation and annihilation of particle pairs eventually ceased. What was left was that small excess of matter, now free to assemble into the building blocks of atoms. Imagine the scene. A fraction of a second after the Big Bang, the universe is an immense, roiling furnace of particles. Matter and antimatter are being born in droves from the tremendous energy, like foam on a churning sea. Immediately, they collide with their counterparts and flash back into energy. For a brief time, it is a state of violent equilibrium, creation and destruction happening in almost equal measure, but not perfectly equal, as it turns out. Perhaps for every billion matter-antimatter encounters, 1 lone matter particle escapes annihilation. As time marches on and the universe cools further, these dramatic pair productions fade away. The sea calms. The remaining particles, that tiny surplus of matter, now find others like themselves to join with. Quarks unite to form protons and neutrons. Protons capture electrons to form hydrogen. In time, those atoms will gather into clouds, ignite as stars, and stars will forge heavier elements, eventually creating planets and, on at least 1 small world, life that can wonder about it all. So what could have caused this slight tipping of the scales? The laws of physics, as far as we know, treat matter and antimatter almost exactly the same. Almost, but not entirely. Subtle differences have been observed. In lab experiments and particle accelerators, scientists have found that certain unstable particles decay in ways that are not perfectly symmetric between matter and antimatter. For instance, some particles can spontaneously transform into their antiparticles and back, a strange quantum oscillation, but they show a minuscule preference for one over the other over time. This phenomenon, known as CP violation, where C stands for charge conjugation symmetry and P for parity symmetry, means nature has a tiny built-in bias, a slight favouring of matter processes over antimatter ones, or vice versa. It's like a coin that is almost fair, but comes up heads just a little more often than tails. The CP violation that we have measured in particle experiments, however, is extremely small, far too small to account for the generous matter surplus we see in the universe now. It's a hint, but not the full answer. The universe's 1 in 1 billion asymmetry suggests a much larger bias must have been at play in those first moments. This has led physicists to hypothesize new particles or interactions that haven't yet been observed. Perhaps in the extreme conditions of the early universe, there were heavy exotic particles that decayed with a preference for producing matter over antimatter. Or maybe neutrinos, those ghostly, nearly massless particles that flood the cosmos, hold clues. As some theories suggest, they might behave differently from their anti-partners in subtle ways that skewed the balance. One idea is that during the early universe's high-energy epochs, like the Grand Unification Epoch or the electroweak phase transition, certain reactions occurred that violated the symmetry between matter and antimatter. In those split seconds, if the universe was out of thermal equilibrium, expanding and cooling rapidly, which it was, and if there were processes that could create more baryons, the particles like protons and neutrons, than antibaryons, and if those processes had CP violation, then the stage would be set for matter to gain an upper hand. These are the conditions outlined decades ago by physicist Andrei Sakharov, required to generate what we call baryon asymmetry, the imbalance of matter over antimatter. To detect signs of this cosmic preference, scientists run high-energy collisions in machines like the Large Hadron Collider, hoping to glimpse new particles that might exhibit asymmetric decays. Others study the behavior of known particles in exquisite detail. For example, comparing hydrogen atoms to antihydrogen atoms to see if they emit the same light spectrum, or measuring whether gravity pulls on antimatter exactly the same way it does on normal matter. So far, no glaring differences have been found beyond those tiny effects already known. Antihydrogen seems to produce the same spectral lines as hydrogen. Antimatter falls downward due to gravity, not up. The mirror image appears remarkably faithful. And yet, somewhere in the depths of physics, an asymmetry, for we are here against what would seem like incredible odds. Another angle to this puzzle is cosmological. Perhaps conditions were set up from the very beginning. Some speculative models propose that the inflaton field, the field thought to drive the brief moment of cosmic inflation, might have decayed in such a way as to create more matter than antimatter. Other proposals suggest an interplay between dark matter and antimatter in the early universe that led to an imbalance. These ideas illustrate the lengths to which scientists will go to explain this cosmic anomaly, because it is so foundational. Without this slight favoritism towards matter, the universe would be lifeless and dark. It's also worth pondering if the universe could have turned out differently. Imagine a universe where the imbalance went the other way, where antimatter dominated and matter was the rare leftover. In principle, such a cosmos would look much like ours from a distance. Antistars made of antihydrogen would burn antihelium in their cores and shine with the same light. Galaxies of antimatter would dance and collide under gravity's pull, just as ours do. But if any pocket of matter ever came into contact with a pocket of antimatter, they would annihilate in a tremendous flash. Thankfully, in our reality, as far as we can observe, the antimatter pockets are essentially gone. The universe we see is almost entirely matter, with only trace amounts of antimatter popping up in high-energy processes or radioactive decays. Even so, scientists have looked for signs of entire antimatter regions, for instance, antihelium nuclei among cosmic rays, or telltale gamma rays that would be emitted where matter and antimatter annihilate along the boundaries of domains. So far, nothing indicates the presence of large antimatter galaxies or clusters. It seems that the matter-antimatter battle in the early universe had a clear winner. Matter, by a narrow margin, but enough to shape everything that followed. This profound question, why does anything exist at all, remains one of the fundamental mysteries of cosmology and particle physics. We have theories and plausible mechanisms, but no definitive proof for any of them yet. The answer is elusive, hidden in the hazy memory of the universe's first moments. To uncover it would be to understand our own origins at the most basic level. Why the fabric of reality favoured the substance that makes us up. For now, we live in the aftermath of that imbalance. Every atom in our bodies, every star in the sky, is a monument to that tiny asymmetry. In the stillness of a clear night, as we gaze upward, we might reflect that all the galaxies glowing softly in the darkness are survivors' trophies, matter that escaped annihilation and went on to form the richly structured cosmos we inhabit. It is a humbling thought that all of this hinged on a minute skew in the laws of nature, one so slight we have to strain to detect it, even with our most sophisticated instruments. As we ponder this cosmic imbalance, we gradually shift our focus to another grand puzzle that emerged as we studied the universe's contents. Once matter existed and gathered into stars and galaxies, we assumed we understood the makeup of the cosmos. But nature had another surprise. The familiar matter, both the regular atoms and even the elusive antimatter, turned out to be only a minor constituent of the universe. When astronomers looked at galaxies and galaxy clusters, they discovered overwhelming evidence of a new kind of unseen mass, far more abundant than all the stars and gas. This hidden mass, dark and mysterious, would overturn our understanding of what the universe is made of. We now venture into the domain of dark matter, the universe's hidden mass, which holds galaxies together, yet remains frustratingly invisible. On a dark, moonless night, far from city lights, the band of the Milky Way arcs overhead, a swath of silvery starlight. To the naked eye, this view might suggest that the universe is filled with stars, and that most of the matter out there shines in one form or another. But as astronomers extended our gaze beyond what eyes can see, they uncovered a startling truth. The vast majority of matter in the universe emits no light at all. This invisible substance is known simply as dark matter. And though we cannot see it or touch it directly, it makes itself known through gravity, the subtle yet persistent tug it exerts on the things we can see. The discovery of dark matter was not a single eureka moment, but rather a gradual realization. As early as the 1930s, Swiss-American astronomer Fritz Zwicky observed distant clusters of galaxies and found an anomaly. He was studying the Coma cluster, a massive swarm of galaxies bound together by gravity. By measuring the speeds at which those galaxies moved within the cluster, he calculated how much mass would be needed to hold them together. The galaxies were moving far too swiftly. If the only mass present was the visible stars and gas, the cluster should have flown apart. Yet it held together, implying there was far more mass present than anyone could account for from the observable matter. Zwicky dubbed this unseen mass Dunkel Materie, German for dark matter. His claims were bold and ahead of their time, and for a while they were largely overlooked or met with skepticism. Decades later, in the 1970s, American astronomer Vera Rubin, along with her colleague Kent Ford, made a compelling case that galaxies themselves harbored a great deal of hidden mass. Rubin studied the rotation curves of spiral galaxies, basically how fast stars and gas orbit the galactic center at various distances. According to Newtonian physics and our experience with the solar system, stars farther from the center of a galaxy should orbit more slowly than those closer in, because the majority of visible mass is concentrated toward the center, just as outer planets move more slowly than inner ones around the sun. But to her surprise, Rubin found that the stars in the outskirts of galaxies were orbiting just as fast, or even faster, than those nearer the core. The rotation curve, instead of dipping down at the edges, stayed flat or rose. This was a huge clue. It was as if an invisible halo of mass surrounded each galaxy, adding gravitational pull on those outer stars and whipping them around at high speeds. There had to be much more mass than what we could see in the stars and nebulae. The evidence for dark matter kept mounting. Observations of galaxies in many clusters, gravitational lensing studies, where light from distant objects is bent by mass on its way to us, forming distorted or multiple images, and precise measurements of the cosmic microwave background radiation all converged on the same conclusion. Approximately 85% of the matter in the universe is dark matter, unseen but pervasive. To put it another way, all the atoms in all the stars, planets, gas clouds, and living creatures combined make up less than 1/5 of the matter content of the cosmos. The rest is this elusive, dark component. What exactly is dark matter? That question has proven exasperatingly difficult to answer. We know a few things by inference. Dark matter does not emit or absorb light, hence dark, and it doesn't interact with ordinary matter through electromagnetism. Otherwise, we would detect its effects in laboratories or see it obscuring starlight. It also seems not to clump on small scales the way normal matter does. For instance, dark matter doesn't form atoms or molecules. It doesn't make small solid objects or people. If it did, we would literally feel it and see it around us. Instead, dark matter forms large, diffuse halos around galaxies and clusters of galaxies, remaining spread out and smooth on scales smaller than a star system. This tells us that dark matter particles, if that's what they are, must move faster or behave differently than ordinary particles in some ways, preventing them from cooling and collapsing into familiar structures. Over the years, scientists have proposed various candidates for dark matter. One leading idea is that dark matter could be a new kind of elementary particle, generically called a WIMP, a weakly interacting massive particle. Such a particle might have a mass on the order of 100 protons or more, making it relatively heavy, but it would interact only via the weak nuclear force and gravity, not via electric charge. Billions of these WIMPs could be streaming through us every second without a single trace, because they mostly ignore normal matter. If two WIMPs happen to collide, they might annihilate each other and produce a faint glow of energy. But because they're so inert, these collisions would be extremely rare in today's low-density universe. Another intriguing possibility is a very light particle known as the axion, which was originally proposed to solve a completely different problem in particle physics, but would fit naturally as dark matter. Axions, if they exist, would be almost ghost-like, able to drift through planets and stars without any effect. Yet in the early universe, they could have been produced in great abundance. Then there are more exotic ideas. Perhaps dark matter consists of primordial black holes. Ancient black holes formed in the first second after the Big Bang from density fluctuations. Unlike normal black holes that arise from collapsing stars, these would be scattered throughout the universe, tiny or large, acting as dark matter. However, various observations have largely constrained how many black holes could exist in this form, and it seems they alone can't account for all the dark matter. So far, despite dedicated searches, dark matter has not been directly detected. Deep underground laboratories housing large vats of liquid xenon or germanium crystals or other detectors have been listening for the faintest ping of a dark matter particle striking an atomic nucleus. These experiments have reported a few tantalizing hints over the years, but nothing conclusive. Particle accelerators, like the Large Hadron Collider, have tried to produce dark matter in high-energy collisions. The signature would be an apparent loss of energy in the debris of a collision, as invisible particles fly out of the detector. Yet, no confirmed sightings have occurred. The dark matter particle, if it is a particle, remains at large. Meanwhile, astronomers continue to study dark matter's effects on large scales. One of the most striking observations supporting dark matter came from a cosmic accident called the Bullet Cluster. This is actually two galaxy clusters that have recently collided with each other. In this clash, the clouds of hot gas from each cluster, which contain most of the normal matter and glow in X-rays, interacted and slowed down, like two cars colliding and crumpling. However, the majority of each cluster's mass, which is dark matter, passed through the collision unaffected, like ghosts. By mapping the gravitational field of this system through gravitational lensing of background galaxies, scientists found that the mass was centered mostly in two lumps that had moved ahead of the colliding gas clouds. In other words, the dark matter of each cluster sailed through the collision without interacting, while the normal matter clumped and slowed in the middle. This separation of matter and mass is hard to explain without something like dark matter. It acts as direct evidence that dark matter has real, physical presence apart from normal gas and stars. Dark matter's existence poses a riddle. It clearly interacts via gravity, shaping the cosmos. Yet it's almost as if it's made of a different set of rules than the matter we know. Some physicists have wondered if perhaps our understanding of gravity itself needs modification on huge scales, an alternative to dark matter known as MOND, modified Newtonian dynamics, and other theories attempt to tweak the laws of gravity to explain galaxy rotations without invoking unseen mass. While these theories can explain certain galaxy behaviors, they struggle to account for the full range of evidence, such as the bullet cluster or the precise patterns in the cosmic microwave background. As of now, the particle dark matter hypothesis remains the most widely supported, albeit unproven, explanation. The influence of dark matter on the cosmos has been profound. In the early universe, after the Big Bang, all matter was nearly uniformly spread out, but tiny fluctuations in density existed. Because dark matter does not interact with light, it began to clump under gravity, even while the normal matter was still a hot plasma coupled to light. By the time the universe cooled enough for normal matter to clump, after atoms formed and light decoupled at the cosmic microwave background stage, dark matter had already formed a complex scaffolding, a cosmic web of filaments and knots across millions of light years. Normal matter then fell into these gravitational wells, lighting them up by forming stars and galaxies. In this way, dark matter served as the architect of cosmic structure, outlining where galaxies would eventually form. Even now, galaxies are thought to sit in vast halos of dark matter that extend far beyond the visible stars. Our own Milky Way, for instance, is surrounded by a roughly spherical halo of dark matter particles, reaching well beyond the edge of the luminous disk, perhaps tens of times more massive than all the stars within. If we could see this dark matter directly, the night sky would look very different. Instead of isolated stars and neat galaxy shapes, we would perceive gigantic, faint clouds of matter overlapping and intertwining. The galaxies we know would be nestled like bright jewels in immense, translucent cocoons of dark matter. And these cocoons are connected by filaments, the tendrils of the cosmic web, along which galaxies are strung like beads on a cosmic string. Today, one of the holy grails of physics is to identify the nature of dark matter. The quest goes on in subterranean labs, in particle colliders, and in astronomical observations of the cosmic large-scale structure. Perhaps a new particle will be discovered that fills this gap. A particle that was abundant in the early universe and still lingers, unseen, in the present day. Or perhaps our theories will need an overhaul. Either way, solving the dark matter mystery will profoundly change our understanding of the universe. Despite its mystery, dark matter has become an integral part of the modern cosmological model. It is the hidden scaffolding that holds the shining tapestry of galaxies together. We know it's there by its gravitational fingerprint on the motions of stars and the bending of light. But until we can capture a particle of it, or observe a definitive interaction, it remains in the shadows. In the quiet of the night, as you ponder the stillness of the cosmos, remember that the darkness itself may not be empty at all. It is full of invisible matter, silently guiding the dance of galaxies. An unseen majority of the universe, dark matter reminds us of how much we still have to learn about what reality is made of. We have peered into the darkness and found it teeming with mystery. Yet, astonishingly, even this dark mass, which outweighs all the normal matter, is not the final word on what fills the cosmos. As we came to terms with dark matter, another, even stranger component of the universe emerged from observations, something that doesn't just sit quietly like dark matter, but instead actively pushes the universe to change. It is a force, or energy, that acts on the grandest of scales, speeding up the expansion of the cosmos. This perplexing phenomenon is known as dark energy, and it constitutes an even larger share of the cosmos than dark matter. To this mysterious force of expansion we now turn. For a long time, the story of the universe's expansion seemed straightforward. Ever since Edwin Hubble discovered in the 1920s that distant galaxies are receding from us, that space itself is stretching, astronomers have known the universe is expanding from an initial hot, dense state. They thought of this expansion like a cosmic explosion gradually slowing down. The mutual gravity of all matter, visible and dark, should be pulling the expansion inward, breaking it over time. The big question for decades was whether that gravity would someday halt the expansion and reverse it into a collapse, or whether the universe would expand forever, slowing asymptotically but never quite stopping. By the 1990s, many expected that careful measurements would show just how much the expansion was decelerating. To gauge the cosmic slowdown, astronomers turned to Type Ia supernovae, exploding stars that serve as standard candles because of their consistent peak brightness. By observing these supernovae in distant galaxies, scientists can measure how fast those galaxies are receding and how far away they are, effectively charting the expansion history of the universe. Two international teams embarked on this quest in the late 1990s. They anticipated that distant supernovae, looking back in time billions of years, would be slightly brighter than expected if the expansion was slowing, meaning those supernovae would be closer than they would be in a freely expanding universe. But when the data came in, it shocked the scientific community. The distant supernovae were dimmer than expected, which indicated they were farther away than our decelerating models predicted. The only sensible explanation was that the expansion of the universe wasn't slowing at all. In fact, it was speeding up. This was a revolutionary finding. The universe, it turned out, was not simply coasting or being gradually reined in by gravity. Something was counteracting gravity on huge scales, causing space to expand faster and faster. The name given to whatever is driving this accelerated expansion is dark energy. It's called dark, not because it is dark like matter, but because it is mysterious and also invisible, pervading space. In a sense, dark energy is a placeholder term for our ignorance. It stands for an effect we observe, but do not yet understand. The discovery of cosmic acceleration earned 3 astrophysicists the Nobel Prize in 2011. But in the years since, the nature of dark energy has remained elusive. What could be pushing the universe outward? One straightforward explanation ties back to an idea Albert Einstein had proposed long ago. In 1917, before Hubble's expansion discovery, Einstein added a term to his equations of general relativity called the cosmological constant. He intended it to balance gravity and yield a static universe, as was the thinking at the time, since the universe was then assumed to be unchanging and eternal on large scales. Once expansion was discovered, Einstein reportedly called that cosmological constant his biggest blunder, because it wasn't needed for an expanding universe. But now, decades later, it seems the cosmological constant, or something very much like it, is alive and well. In Einstein's theory, a cosmological constant represents an intrinsic energy of space itself. Even the vacuum of space has a latent energy that produces a repulsive effect on large scales. If this constant is greater than zero, it can drive acceleration as observed. So one possibility is that dark energy is simply this cosmological constant, an unchanging property of space-time. When we plug such a constant into our cosmological models, we get a universe that fits the supernova data and many other observations, including the detailed patterns in the cosmic microwave background and the distribution of galaxies. In this model, dark energy makes up roughly 68% of the total energy content of the universe, dwarfing dark matter, about 27%, and ordinary matter, about 5%. This means most of what's out there isn't matter at all, but a mysterious energy associated with empty space. However, calling it a constant doesn't explain why it has the value it does. The cosmological constant solution also brings its own deep puzzles. The value of dark energy density inferred from observations is astoundingly small in particle physics terms, yet non-zero. Theoretical calculations of vacuum energy from quantum fields, if taken at face value, would predict a cosmological constant many orders of magnitude larger, so large that the universe would have blown apart instantly. Why then is the dark energy so tiny, yet not exactly zero? This is sometimes called the cosmological constant problem, one of the biggest unsolved problems in physics. Some have invoked the anthropic principle. If dark energy were much larger, galaxies couldn't form, and we wouldn't be here to observe it. So perhaps we exist in a universe with a life-permitting value, by cosmic coincidence, among a multiverse of different values. It's a conjecture that speaks to how puzzling this is. Another possibility is that dark energy isn't constant at all, but rather a dynamic field that changes over time, sometimes referred to as quintessence. In this picture, what we call dark energy might be a slowly rolling energy field that permeates space. Early in cosmic history, its effects might have been negligible, but as the universe expanded and matter diluted, this field's energy came to dominate and drive acceleration. If true, the acceleration might not be uniform. It could even eventually stop or reverse if the field evolves. Scientists are looking for clues to this by examining the expansion rate at different epochs. For instance, upcoming surveys and telescopes We'll map millions of galaxies and supernovae to see if the push of dark energy has changed over cosmic time. Regardless of what dark energy is, its presence has huge implications for the fate of the universe. In a dark energy-dominated universe like ours, the expansion will continue to accelerate into the future, at least as long as dark energy remains repulsive and roughly constant. Distant galaxies that are not bound to us, outside our local group, will recede faster and faster, eventually crossing horizons beyond which they can no longer be seen or influenced. Hundreds of billions of years from now, observers in our galaxy, or its merged descendant, might see nothing but a dark, empty expanse beyond, all other galaxies having slipped out of view. The universe will become colder and more isolated as this expansion carries everything apart. Some more extreme speculations consider if dark energy's strength might increase over time. In a scenario dubbed the Big Rip, the repulsive force grows so strong that it eventually shreds all bound structures, galaxies, solar systems, planets, even atoms, torn apart by accelerating expansion. Fortunately, current observations suggest we are not headed for such a catastrophic fate, as dark energy appears consistent with a constant vacuum energy, rather than something that grows without bound. If it's truly a cosmological constant, the expansion will approach a steady exponential rate. That leads to an ever emptier universe, but not an outright rupture of matter. On the other end of possibilities, some theorists wonder if dark energy might someday decay or change sign. If, for instance, dark energy weakened or became attractive in the far future, it could slow the expansion or even trigger a collapse, a big crunch. While there's no evidence for this now, the truth is, we have only observed dark energy's effects for a relatively brief window of cosmic time, the last few billion years, so we cannot be certain of its long-term behavior. Astronomers and physicists are actively seeking more information about dark energy. The cosmic microwave background observations by satellites like Planck have pinned down the amount of dark energy with precision. Large surveys of galaxies, mapping how structures cluster and grow, provide independent evidence of acceleration. New telescopes like the James Webb Space Telescope, the Vera Rubin Observatory, with its vast sky survey capabilities, and the upcoming space missions like Euclid and the Nancy Grace Roman Telescope are poised to offer further insights. They may not see dark energy directly, but by measuring the geometry and expansion of the universe with exquisite accuracy, they will test whether dark energy behaves exactly like a cosmological constant or shows any hints of variation. Despite these efforts, dark energy remains deeply enigmatic. In a way, it feels almost philosophical. Empty space itself has energy and dominates the universe. It calls to mind that even the vacuum is not truly nothing. It has this hidden influence that shapes everything. In total, when we combine dark energy and dark matter, we find that around 95% of the cosmos is mysterious and invisible to us, except through its effects. We find ourselves living in a universe where the substances we have understood and touched, like atoms, light, planets, stars, are just a thin frosting on a very strange cake. How do we live in such a universe? The same as always, bound by gravity locally on our Earth and solar system, unaware in daily life of the grand cosmic expansion. We only notice dark energy in the redshifts of far galaxies, and the equations of cosmologists. Yet, its reality means that the universe's largest scale evolution is governed by a still unidentified agent. There's a poetic quality to that, an invisible force filling the emptiness of space, controlling the destiny of galaxies. The introduction of dark energy into our cosmic story is a reminder that as much as we have learned, there may be fundamental elements of reality we have yet to grasp. It humbles us to think that even now, the universe holds surprises that can overturn assumptions. It was only a little over 2 decades ago that we even realized this acceleration was happening. In the meantime, we continue to measure and hypothesize. Perhaps one day we'll detect some particle or effect that reveals the nature of dark energy. For example, some theorists speculate about dark energy particles or connections between dark energy and other forces. Others explore if modifications to general relativity could account for cosmic acceleration without invoking a new energy component. As we close this chapter on dark energy, we acknowledge it as one of the universe's foremost enigmas. The night sky, filled with countless galaxies, is also filled with an unseen pressure, pushing those galaxies apart. In silence, it operates, stretching the very fabric of the cosmos. From the sweeping influence of dark energy across the universe, our journey now shifts to a very different kind of cosmic mystery. Instead of something that is smooth and diffuse across all of space, we turn to objects that are intensely concentrated, places where gravity crushes matter into an abyss from which not even light can escape. These are the black holes, the secretive abysses scattered throughout the cosmos, challenging our understanding of physics at every turn. Imagine a star many times more massive than our sun, shining brightly for millions of years. Eventually, the day comes when it has burned through the nuclear fuel in its core, no longer able to support itself against its own immense gravity. The core begins to collapse. In a breathtakingly short time, the star's center implodes, and a supernova explosion tears the outer layers apart. But deep at the heart of that explosion, something extraordinary has formed. The core has been crushed to such density that it creates a black hole, a region of space where gravity is so intense that nothing, not even light, can escape its grasp. Black holes are, in a sense, the ultimate victory of gravity over all other forces. The boundary around a black hole, beyond which nothing can return, is called the event horizon. It's not a physical surface. You wouldn't crash into it. It's simply the point of no return. Once you cross that boundary, the pull inward is inexorable. For a small black hole formed from a star, that boundary might be only a few kilometers across. All the mass of a star squeezed into a sphere the size of a city. For a supermassive black hole, like the ones lurking in the centers of galaxies, the event horizon could span millions of kilometers. But big or small, the defining feature is the same. Cross that line, and escape becomes impossible. What lies inside a black hole? According to Einstein's general theory of relativity, if one were to follow the physics to its conclusion, the mass of a black hole continues to collapse all the way down to a point of infinite density and infinitesimal volume, a singularity. Space and time themselves are so warped by gravity in this regime that our equations break down. Much like the Big Bang singularity, the center of a black hole represents a place where we need new physics, a theory of quantum gravity, to fully understand what's happening. It could be that the singularity is not truly a point at all, but rather our best description falls short. Some theories suggest that quantum effects might create a sort of extremely compact but finite core rather than an infinite density, but without being able to observe directly or experiment, we're left with educated guesses. To an outside observer, a black hole's presence can only be inferred by its influence on surrounding matter or light. We cannot see the black hole itself. It is, by definition, black. But we can often see a swirling disk of hot gas and dust, known as an accretion disk, that spirals into the hole. As matter falls in, it heats up and glows, sometimes outshining entire galaxies in the case of quasars, where a distant galaxy's central supermassive black hole is voraciously consuming material, producing a brilliant beacon visible across the universe. We also observe stars in orbit around invisible centers, moving so fast that only a very compact, massive object could be responsible. This is how we identified the supermassive black hole at the center of our Milky Way. Over years, astronomers tracked stars whipping around an unseen mass at incredible speeds, deducing that about 4 million suns worth of mass must be packed into a space no larger than our solar system. That could only be a black hole. And indeed, in 2022, the Event Horizon Telescope collaboration released a radio image of the glowing surroundings of this black hole, Sagittarius A, confirming its shadow-like silhouette as predicted by general relativity. Black holes come in different sizes. Stellar mass black holes form from collapsing stars and might weigh a few to dozens of times the sun's mass. Supermassive black holes reside in galaxy centers and can range from millions to billions of solar masses. How they grew so large, especially those found in the early universe, is an ongoing area of research and mystery. Some might have formed from the merging of many smaller black holes and gas accretion over eons. Others could have originated from giant primordial seeds. There's also evidence for intermediate mass black holes, bridging the gap between stellar and supermassive, though they are harder to find. One of the fascinating and counterintuitive effects near a black hole involves the flow of time. If you could watch a clock falling towards a black hole from a safe distance, you would see that clock tick slower and slower as it got closer to the event horizon. At the horizon, time for that clock, as seen from your perspective, would appear to almost freeze. The light from the clock and the clock itself would gradually fade and redden, taking longer and longer to reach you, effectively never showing the clock cross the horizon. In reality, for the clock itself or someone riding with it, time flows normally, and they would pass the horizon without noticing anything particularly special at that exact boundary. Especially if the black hole is large, the tidal forces at the horizon could be negligible. But once inside, they would be on a one-way journey inward, with all paths in space leading inevitably to the center. For a smaller black hole, the journey would be even more harrowing. Before even reaching the horizon, the difference in gravity between head and feet would stretch and compress a human traveller in a process colloquially known as spaghettification. The person would be torn apart into a stream of atoms long before approaching the singularity. For a supermassive black hole, by contrast, one might cross the horizon unharmed, since the tidal forces at the horizon could be mild, only later encountering stronger gradients deeper inside. In either case, no signal can escape back out to tell the tale. Black holes challenge our understanding of physics with the famous information paradox. When something falls into a black hole, say a book or a planet, what happens to the information that described that object, the particular arrangement of its particles? According to quantum physics, information cannot be destroyed. But if the book passes the horizon, from our viewpoint, it's essentially gone. Stephen Hawking discovered that black holes aren't completely black. They emit a very faint thermal radiation due to quantum effects near the horizon, what we now call Hawking radiation. This means black holes can slowly evaporate over incredibly long timescales, radiating away their mass. For an enormous black hole, this evaporation is negligible over the age of the universe. But for small ones, it could be significant. If a black hole completely evaporates, what becomes of all the information that fell in? Hawking's initial calculation suggested the information might be lost forever, encoded only in featureless thermal radiation, a result that deeply troubled physicists because it conflicts with quantum theory's tenet of information conservation. This sparked decades of debate and work on the black hole information paradox. Many now suspect that the information is not truly destroyed, but somehow imprinted in the outgoing radiation in a highly scrambled form, or perhaps retained in a remnant. Ideas like the holographic principle have been proposed, suggesting that all the information about what has fallen in might be encoded on the event horizon's surface, much like a hologram encodes a 3D image on a 2D plate. The jury is still out on the resolution, making this one of the cutting-edge enigmas bridging gravity and quantum physics. Another mystery involves what really happens at the very core. Does the singularity signify the end of space-time, or could it be a bridge to something else? In science fiction and speculative physics, black holes are sometimes imagined as gateways. If one were connected to another via a tunnel in space-time, a wormhole, perhaps travel or transport to distant places or even other universes could occur. Wormholes captivate the imagination, but we have no evidence they exist, and our theoretical constructions of them usually require exotic matter to hold them open, matter with negative energy, which has not been found in nature in the necessary form. Still, it's a tantalizing idea. Could a black hole be part of a cosmic pathway to elsewhere? If the universe is strange enough, perhaps the singularity is not an end, but a portal. Some theorists have even whimsically suggested that a black hole in our universe could spawn a baby universe on the other side, making every black hole a potential Big Bang of a new cosmos. These ideas remain in the realm of speculation, serving more to stimulate new ways of thinking about gravity than as immanent explanations. Observationally, we are in a golden age of black hole astronomy. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, first detected the telltale chirp of gravitational waves from two black holes merging far away. Those waves, ripples in space-time itself, travelled for over 1 billion years before gently jostling the detectors on Earth, revealing an event that until then was completely dark to us. Since that first detection, many more gravitational wave signals have been observed, painting a picture of a universe where black holes frequently collide and merge. Each detection confirms that black holes are real, common, and that Einstein's description of these extreme events is remarkably accurate. And then there are the direct images. In 2019, the Event Horizon Telescope project unveiled the first ever image of a black hole's silhouette, the supermassive black hole in galaxy M87. That image showed a glowing ring of superheated gas and dust surrounding a circular dark patch, the shadow of the event horizon, where light is swallowed. It was a monumental technological achievement, essentially turning the Earth into a giant radio telescope array to achieve the needed resolution. Looking at that fuzzy ring, we are witnessing the imprint of a black hole on its environment, a sight once thought impossible. These observations have confirmed what was once purely theoretical. Yet paradoxically, as black holes move from the realm of theory to observation, the fundamental mysteries they pose become even sharper. We know they exist. We can measure their mass and spin. We can even map out how they warp space around them. But we still don't truly know what happens at the very edge and beyond. Black holes, in a way, are like cosmic mirror images to the Big Bang. The Big Bang was an explosion of space-time outward, a singular origin giving rise to all we see. A black hole is an implosion of space-time inward, a possible singular endpoint for a chunk of the cosmos. Perhaps by understanding one, we will better understand the other. Some scientists even speculate that the conditions near a black hole could mimic the early universe in reverse, and that clues to quantum gravity might emerge from studying black holes carefully. As we float in the thought of these gravitational abysses, there is an almost serene awe to them. These are places where the normal order of time and space is upended, where the known laws of physics reach their limits. And yet, black holes themselves are a natural outcome of those same laws. They are part of the life cycle of stars and the fabric of galaxies. Space is peppered with them. Tens of millions, likely in our Milky Way alone, quietly hiding unless they interact with nearby matter. They are not monsters roving to devour everything. They simply are, like cosmic punctuation marks that accent the story of the universe. When gazing into the night, we cannot see a black hole's darkness, but we might see a quasar twinkling, or the motions of stars that dance to an invisible tune. Those are the subtle signs of these dark giants at work. The quiet enigma of a black hole invites us to reflect on the extremes that nature offers. Having delved into phenomena that bend space and stop light, we finally turn to a mystery that underlies all experiences: the flow of time itself. Black holes have shown us that time can be stretched and slowed, but they do not answer why time only moves forward and never in reverse. For our final exploration, we consider time's arrow, the one-way direction of time, and why our universe has a past, present, and future that are irrevocably ordered. Time. It is ever present in our lives, flowing from one moment to the next. We sense it in the progression of the days and seasons, in the aging of our bodies, in the memories we hold of yesterday, and the uncertainty of tomorrow. There is an intrinsic direction to these experiences. We remember the past, but not the future. We grow older, never younger. A broken cup does not spontaneously reassemble itself. This one-way flow is often taken for granted, yet it is one of the most profound aspects of the universe. We call this the arrow of time, the idea that time has a preferred direction, from past to future, that gives rise to the distinction between what has happened and what is yet to come. Interestingly, if you look at the fundamental laws of physics, the equations that govern how particles move or how forces act, most of them are time-symmetric. That is, if time were to run backward in those equations, the processes would still make sense. A planet orbiting a star follows the same gravitational equations, whether time runs forward or backward. A collision between two particles looks just as valid in reverse. At the microscopic level, physics doesn't seem to mandate an arrow of time. And yet, when we scale up to the world we experience, the arrow is unmistakable. So where does this arrow come from? The answer lies in a concept called entropy, which is a measure of disorder or randomness. The second law of thermodynamics, a bedrock principle of physics, states that in an isolated system, entropy tends to increase, or, at best, stay the same. It never decreases on its own. This law introduces an asymmetry between past and future. The past is a state of lower entropy, the future a state of higher entropy. In simpler terms, things naturally move from order to disorder. You can mix milk into your coffee, and soon you have a uniformly blended drink, more disordered than two separate layers. But you'll never see the milk spontaneously separate out again. A drop of ink spreads in water and will not gather itself back. These processes are irreversible. They define a direction in time. Our universe, as it turns out, began in a very low entropy state. At the moment of the Big Bang, and particularly a bit later when matter and radiation decoupled, conditions were extremely hot and dense, but also very uniform. Uniformity might sound like disorder, but in gravitational terms, it was an orderly state. All of space filled almost evenly with energy. Over time, gravity drew matter together into clumps, stars, galaxies, clusters, increasing the entropy associated with gravitational degrees of freedom. Meanwhile, other processes increased entropy as well. Stars burned fuel and radiated heat, mixing energy into space. Structures formed and then decayed. The entropy of the universe has been rising ever since that smooth beginning. The arrow of time, then, is intimately connected to these initial conditions. Time points forward in the direction of increasing entropy, because the universe started with unusually low entropy. This raises a deeper question. Why was the entropy of the early universe so low? Was it just a fortunate accident, or is there some principle that set those initial conditions? This is sometimes called the past hypothesis by philosophers of physics, the assumption that the universe started in a special low entropy state. Some theorists speculate that if our universe is part of a multiverse or a cyclic model, perhaps what we call the Big Bang was a low entropy rebirth that establishes an arrow for what follows. Others argue that we might just have to accept a low entropy start as a given, something perhaps dictated by a deeper theory of cosmology yet to be discovered. Whatever the cause, that low entropy beginning is why we have a coherent arrow of time now. It's why we can define a before and after. If the universe were in thermal equilibrium, maximum entropy, everywhere and at all times, there would be no meaningful flow of time. Every moment would be as jumbled as every other. It is the gradients and changes, moving from one state to a slightly more disordered one, that carve out what we perceive as time's passage. We also find arrows of time in other domains, and they all align with the thermodynamic arrow. There is the psychological arrow of time. Our minds recall the past and not the future, and we anticipate what's to come. This is likely because our brains themselves are physical systems subject to entropy. The act of forming a memory involves creating order, storing information about an event that has happened, which correlates with that event when entropy was lower. By the time the event is done and recorded in our brain, entropy has increased. The reason we can't remember the future is that the future hasn't happened yet. It hasn't left an imprint or record, because entropy will increase in bringing it about. There's also the radiative arrow. When you drop a pebble in a pond, ripples spread outward. You don't see them suddenly converge into a splash. Sound from a loud noise travels outward and dissipates. We don't hear random room noise concentrating itself into a sharp bang. This too is a reflection of entropy. Energy disperses, spreading outwards and becoming more distributed among degrees of freedom rather than gathering itself back up. Even on cosmic scales, we see an arrow. The universe expands and cools, moving from a hotter, more organized state, all matter and radiation in a dense ball, to a cooler, more diffused state. Interestingly, if gravity were the only factor, a contracting universe might reverse some arrows. Structures might become less clumped if everything fell together, but other processes would still generate entropy. Some have imagined a scenario in which time's arrow could reverse in a contracting phase of the universe. But if that were to happen, it would likely be in a context where no observers like us could survive to experience it, and it's deeply speculative. It's important to note that the arrow of time is a statistical statement. It's not that entropy absolutely cannot decrease. It's that it's overwhelmingly unlikely to do so in a closed system. On extremely rare occasions, small parts of a system might fluctuate into lower entropy momentarily, like a few molecules of gas in a box randomly all moving to one corner briefly. But for macroscopic systems, such random decreases are effectively impossible within the age of the universe. Thus, we see a consistent arrow. This one-way flow has significant implications. It gives us the concept of cause and effect. Causes precede effects. You light a candle, cause, and then the flame grows, effect, not the other way around. That ordering arises from the conditions of lower entropy in the cause leading to higher entropy in the effect. The burning of candle wax increases entropy by releasing heat. If somehow entropy could decrease reliably, causes and effects might blur, and physics would get very strange indeed. Time's arrow also guides the fate of the cosmos. As entropy increases, the universe heads toward a state sometimes referred to as heat death. Not literally heat, but a state of maximum entropy where all gradients are gone. In such a far future scenario, all stars have burnt out, matter is spread thin, black holes have evaporated, and what remains is a thin gas of particles and photons at uniform temperature. With no differences left to drive processes, change essentially ceases, and time, in a sense, loses its meaning because there are no events to mark it. This would be the ultimate entropic equilibrium, the end of the arrow, where the tip has struck and can go no further. It's a bleak, yet serenely quiet vision of the cosmos's future, trillions upon trillions of years from now. Is there any way the arrow could be different? Some speculative ideas suggest that perhaps on the other side of the Big Bang, if such a thing exists, time might run in the opposite direction. For example, a universe contracting towards a big crunch might have an observer who perceives time forward in what we'd call the reverse direction, with their own past being our future. These ideas are exotic and largely untestable at the moment, but they arise naturally when pondering symmetrical laws and initial conditions. If the Big Bang was truly the beginning of time, however, then the arrow as we know it is simply a feature of our universe from start to finish. The arrow of time links back to everything we have explored. Black holes, for instance, increase entropy when they form. They are actually maximal entropy objects for a given region. That's one reason they are very stable endpoints for matter. When they evaporate, they spew out entropy in the form of Hawking radiation. The formation of structure in the universe, galaxies, stars, planets, was enabled by the fact entropy could rise. Gravitational clumping raised entropy from the smooth initial state. The tiny asymmetry that left us with matter rather than antimatter also ties into entropy. The annihilation of particles produced a flood of radiation, entropy, and left a small ordered excess of matter that would go on to form complex structures, later increasing entropy again as those structures burn energy. And of course, the question of why the universe started in such an ordered state dovetails with the question of what, if anything, preceded the Big Bang. If there was something before, perhaps the arrow of time emerged then, or perhaps time as we understand it didn't exist. It's a reminder that many of these deep questions are intertwined. As we contemplate time's arrow, we might find a kind of comfort in its steady progression. The irreversible flow of time is what allows the universe to evolve and life to unfold. Every experience, every moment of beauty or discovery is set against the backdrop of time moving forward. The fleeting nature of time can make those moments precious. Now, as we near the end of this journey through cosmic enigmas, think of the vast timescales we've touched upon. From the split-second mysteries before the Big Bang to the unimaginable future of the universe. Our human lives occupy but a tiny sliver of cosmic time, and yet we are intimately a part of this grand unfolding story. We inherit the past, the ashes of ancient stars in our blood, the memory of the early universe in our atoms, and we step into the future, carried by time's current. In the quiet of a reflective night, these mysteries of time and the cosmos can swirl in our thoughts. We don't yet have all the answers. Perhaps we never will. And in a way, that is all right. The unknown has its own allure, inviting us to explore further, to question deeper. The universe, with all its unanswered questions, presents a tapestry of wonder that we slowly unravel, thread by thread, even as we realize it may be infinite. We take a moment now to pause and reflect, closing this chapter of our journey, not with a conclusion, but with a calm breath. In this peaceful pause, the universe's unanswered questions linger like distant stars, quietly beckoning us onward into the unknown. Under the vast expanse of a clear night sky, a timeless question stirs in the human mind. Are we alone in the universe? Countless stars shimmer above, each a sun in its own right, many with planets circling in the dark. We gaze upward and wonder if, on some distant world, orbiting one of those stars, another being is also looking up and asking the very same question. The silence of the night sky is profound. We have been listening for voices among the stars, but so far we have heard nothing but the faint, natural hum of cosmic noise. In this great, quiet darkness, the absence of an answer itself becomes a mystery. Why, in a universe so vast, have we found no sign of anyone else? This puzzling silence is often called the Fermi paradox, a reminder that something about our expectations and reality is not quite adding up. Imagine standing beneath a sky filled with billions of galaxies, each galaxy containing billions of stars. Our own Milky Way is just one such galaxy, with hundreds of billions of stars. In recent years, we have learned that many of these stars host planets, some of them roughly Earth-sized, some in the so-called habitable zone, where temperatures might allow liquid water. By sheer numbers alone, it seems almost inevitable that life has sprouted elsewhere in the cosmic ocean. If even a tiny fraction of stars had planets with life, and a tiny fraction of those gave rise to intelligent beings capable of technology, there could be many civilizations scattered through the Milky Way. And if some of those civilizations have been around longer than we have, perhaps millions of years longer, their capabilities might be far beyond our own. They might have learned to travel between the stars, or at least to send signals across the light years. And yet, as far as our best instruments can tell, the universe remains eerily quiet. We see no ships in our skies aside from our own, and we intercept no unmistakable interstellar radio messages in the vast sea of static. This disparity between the expectation of numerous advanced civilizations and the lack of evidence for even one has been a subject of wonder and perplexity for decades. In the mid-20th century, Physicist Enrico Fermi famously captured this conundrum in a simple, poignant question. Where is everybody? In a cosmos so old and so expansive, one might think at least one other voice would have spoken up by now. One other beacon would have shone out in the darkness. But our searches so far have found nothing definitive. No alien beacons, no extraterrestrial probes openly visiting our world. Only silence and mystery. The mind wanders through possible answers. Perhaps life itself is exceedingly rare, and we truly are alone, or nearly so. The only living beings for countless light years. Perhaps the conditions that allowed life to spark on Earth are a cosmic fluke, a once-in-a-galaxy stroke of luck, and no other island in the cosmic sea has ever blossomed with life quite like ours. If that were true, then the night sky might indeed be empty of voices, and we would bear the heavy responsibility of being the universe's sole witnesses to itself. This thought is both awe-inspiring and profoundly lonely, that in all the cosmos, in all its vastness, we might be the only ones to appreciate its beauty. On the other hand, maybe life is common, sprouting on many worlds as easily as weeds in a field. But the jump to intelligent, technologically capable life is rare. It took roughly 4 billion years of evolution on Earth for one species to arise that could build radios and rockets. Perhaps on most living worlds, life stays simple, like microbes or tiny plants and animals, never organizing into societies that look up at the stars. There could be planets teeming with alien forests and seas full of strange creatures. But no one in those worlds ever invents a telescope or wonders about life beyond their sky. If that's the case, the galaxy might be full of life and yet devoid of starfarers, with Earth one of the few places where curiosity evolved into capability. Another possibility is that intelligent civilizations do arise elsewhere, perhaps fairly often, but they are short-lived. Maybe the universe has had many societies that achieved science and technology, only to fade out or self-destruct before they could reach across the stars. Imagine civilizations rising and then going extinct like brief flames in the darkness, through wars, environmental collapse, or other catastrophes, snuffed out by the same intelligence that allowed them to flourish. If such great filters await every young civilization, perhaps most never last long enough to make contact with neighbors. Our radio searches might be listening in between the static of civilizations that came and went eons ago. The cosmos could be littered with the silent remnants of those who failed to endure, with no one left to answer our call. Or could it be that advanced civilizations are out there but choose not to reveal themselves? Some have imagined a kind of cosmic quiet zone or zoo scenario. Perhaps Earth is being deliberately left alone or observed from afar, as if we were creatures in a cosmic wildlife preserve. In this line of thought, older civilizations might follow a rule of non-interference, waiting for us to reach a certain level of maturity before making themselves known. If that were true, then the silence is intentional, a quarantine of sorts, leaving us to grow without outside influence. It's a whimsical idea, more speculation than evidence, but it paints an interesting picture. The universe as a grand, quiet stage on which we are developing until the time is right for a grand reveal. Then again, maybe the fault lies not in the stars, but in our own methods. We have only been searching for a short time, in a limited way. Radio telescopes have only listened intently for a few decades, scanning narrow bands of the radio spectrum. The signals we seek, deliberate radio beacons or obvious signs of technology, might not be how an alien civilization would communicate, or they might be far more subtle or advanced than we can currently recognize. Perhaps extraterrestrial intelligences use technologies beyond radio waves, signals that our science doesn't yet know how to detect. Or maybe they communicate very infrequently, or in codes we don't understand, or their signals have weakened to indistinguishability by the time they reach us over such immense distances. Consider also the vastness of time. The universe is nearly 14 billion years old, while our civilization has been capable of radio for barely more than a century. A blink of an eye. It could be that other civilizations did exist millions of years ago, but died out long before we came along, or that others will arise millions of years in the future, long after we are gone. The chances of two technological civilizations being close neighbors, not only in space, but in overlapping time, might be very small. Perhaps the galaxy has only ever had a few spacefaring cultures, active at any given epoch, separated by enormous gulfs of time and never overlapping. We might simply be early or late to the party, finding ourselves in a quiet moment between cosmic events. As we search for answers, we have also begun trying to make ourselves known. We have sent faint signals of our own into space, radio waves carrying music and speeches and the simple ping of radar dishes. We have even attached our greetings to robotic emissaries like the Voyager spacecraft, now drifting indefinitely between the stars with golden records of Earth sounds and imagery. So far, these efforts have been met with silence. We point our radio ears at the sky and hope for a deliberate signal, an unmistakable pattern that stands out against natural cosmic noise. Each time our instruments detect a strange pulse or an unexplained blip, for a moment, hearts race. Could this be it? Could this be the long-awaited hello from an alien mind? But each time so far, the mystery has resolved into something natural or human-made. The rhythmic beat of a pulsar, the hiss of a distant quasar, or simply interference from our own technologies. And so, under the silent stars, humanity continues to wonder. There's a certain romance in the question itself, the idea that perhaps, across the cosmic gulf, there might be others, beings with their own thoughts and dreams, gazing at their night sky and feeling the same longing for connection. Perhaps they too have stories and art, science and questions, and a deep desire not to be alone in the dark. The paradox of the silent sky leaves us with not just one question, but many. If we are alone, what does that mean for our place in the universe? If we are not alone, Why can't we find evidence of the others? Even without an answer, the question spurs us onward. It encourages us to keep listening, to keep searching, and to reflect on the nature of life and intelligence. In the cosmic perspective, life, especially intelligent life, might be exceedingly precious. Perhaps one day the silence will be broken, and we will learn that the cosmic dark was not truly empty. Perhaps a faint signal will someday be detected unmistakably from a distant civilization, or perhaps our descendants will one day find relics or ruins on some far-off world, proving that someone else was there. Until then, the night remains quiet, and we remain watchful, filled with hope and curiosity. Under the canopy of stars, one cannot help but feel both tiny and grand. Tiny because we are but specks in an immense cosmos, and grand because we have minds able to ponder that cosmos. In that reflective silence, it strikes us that maybe the first step to answering whether we are alone is understanding ourselves and our own origin. After all, our quest to find others begins with the story of how we came to be. And so, our journey now turns inward, back through time to the early earth, to explore how the spark of life first took hold on our world, a mystery that may hold clues to life's existence elsewhere in the universe. Turn the clock back some 4.5 billion years, and Earth is a very different place. In its infancy, our planet is hot and volatile, a world born of fire and chaos. Meteors rain down under a toxic sky. Volcanoes erupt with fury, spilling lava across a barren landscape. There are no plants, no animals, not even a single microbe, just rock, water, and a restless young atmosphere. Over time, as the bombardment from space eases and the planet cools, rains begin to fall, forming the first seas in craters and lowlands. Lightning forks across the sky in violent storms, striking the surface and the nascent oceans. In those early waters, warmed by geothermal heat and stirred by tides and tempests, a quiet chemistry starts to unfold. Simple molecules that permeate the young seas begin to link together into more complex forms. The ingredients are humble: water, carbon, simple gases like methane and ammonia, and energy from sunlight and lightning. Yet, given time and the vastness of the early oceans, these ingredients mingle and react in countless ways. It's a scene of creative simmering. Warm pools on ancient shorelines evaporate and concentrate the chemicals within them. Deep undersea hydrothermal vents release hot, mineral-rich fluids into the ocean, creating gradients of energy and chemistry. In these niches, lifeless matter dances a slow dance, forming amino acids, nucleotides, and other organic compounds, the fundamental building blocks of biology. Scientists have found that when we mimic those early Earth conditions in the lab, mixing water with primitive atmospheric gases and adding sparks of electricity, organic molecules appear spontaneously. Amino acids, the pieces of proteins, form unbidden in the flasks. It seems that nature, given the right conditions, readily forges the pieces needed for life. Even in space, we see evidence of life's precursors. Meteorites that have fallen to Earth carry amino acids and complex carbon molecules, and telescopes have detected organic compounds drifting in interstellar clouds. The cosmos is full of the raw materials of life, as if the universe has been stockpiling ingredients, waiting for the right moment to cook up something truly novel. But having the ingredients is one thing. Assembling them into something that lives is another. At some point in those primordial seas, a line was crossed, a threshold between chemistry and biology. No one yet knows exactly how or when it happened, but we can imagine one possible scenario. Perhaps in a sun-warmed pond or around a deep-sea vent, a set of molecules by chance arranged itself into a structure that could make copies of itself. It might have been a primitive strand of genetic material, similar to RNA, carrying information, or maybe a simple membrane formed a tiny bubble, trapping a mix of chemicals inside that began to react in cycles, growing and splitting, a protocell of sorts. Whatever it was, it marked the birth of something new on Earth, the very first glimmer of life, a tiny, fragile entity that could grow, replicate, and evolve. It probably wasn't alive in the way we'd recognize today. No heartbeat, no crawling creature, just a microscopic bit of matter that had the remarkable property of copying itself and thus could carry on its pattern. Once that spark was lit, it never went out. That first proto-life, or perhaps a handful of different little experiments by nature, gave rise to a lineage of organisms. Over countless generations, those simplest living molecules refined themselves, became more efficient and more elaborate. They learned, in a sense, to harness energy and build more complex structures. They joined together into the first true cells. By around 3.5 to 4 billion years ago, only a few 100 million years after Earth cooled enough to have oceans, there were primitive single-celled life forms populating the waters. We find hints of them today in ancient rocks, faint chemical fingerprints and fossilized colonies of microbes known as stromatolites. These early organisms were likely similar to bacteria. They fed on simple chemicals, perhaps thriving around those deep-sea vents or in sunlit shallows. For an unimaginably long time, life remained at this microscopic stage. For billions of years, Earth was a planet of microbes, unseen but tirelessly active, slowly transforming the world around them. Some eventually learned to capture sunlight for energy, breathing out oxygen
and fundamentally changing the atmosphere. A great revolution that paved the way for more complex life to breathe and thrive.
The transition from that first spark to the rich tapestry of life we see today was a slow cosmic symphony, each movement building on the previous one. Tiny cells evolved into more complex cells with specialized parts. Much later, some of those cells joined together to form multicellular organisms, setting the stage for larger and more intricate beings. Eons passed. Continents shifted. Climates swung from hot to frozen, and life met catastrophes and rebirth in cycles of mass extinctions and diversifications. Yet through it all, life persisted and adapted, diversifying into myriad forms. Every living thing on earth today, from the mightiest tree to the smallest insect, from the whale in the ocean to us humans, gazing at the stars, traces its lineage back to that primordial beginning. We carry in ourselves the chemical echoes of the ancient ocean, the DNA code that guides every creature is written in an alphabet first crafted by those earliest life forms. It's humbling to realize that the entire biosphere of our planet is essentially one extended family, descended from a common origin. In a sense, that first cell is still alive today, its spark passed like a baton from generation to generation through every living being across billions of years. Yet, despite all we have learned, the exact recipe for that first spark of life remains elusive. Scientists have been striving for decades to understand how non-life transitioned into life. We've created simple cell-like bubbles in laboratories and watched complex organic molecules form under plausible prebiotic conditions. But bridging the gap all the way to a self-replicating, evolving organism remains one of the great unsolved puzzles. It is as if we have all the pieces of a jigsaw scattered on a table. Amino acids, sugars, lipids, nucleotides, and we can assemble some sections, but the full picture still escapes us. Was it a gradual accumulation of many small steps, each making the next one more likely? Or was it a rare, fortuitous event that happened only once in a trillion chances? Did life begin in one specific location, a singular, warm little pond, as Charles Darwin mused? Or did it spark in multiple places, with only one lineage enduring to populate the planet? We simply don't know. Each new discovery, whether a hint of ancient life in a rock or a clever new experiment in the lab, gives us additional clues, yet often raises new questions. The origin of life remains a profound mystery, a story still mostly hidden in the haze of deep time. Beyond Earth, the question of life's origin takes on an extra layer of wonder. If the universe readily provides the ingredients for life, did the miracle of assembly happen elsewhere too? Mars, for instance, was once a warmer, wetter world. We see ancient riverbeds and lake bottoms etched into its surface. Could life have gotten started on Mars in that early era, only to perish as the planet later froze and dried? Perhaps some tiny Martian microbes still survive, clinging on in pockets of subsurface ice or salty brine, enduring in the dark. Meanwhile, on Jupiter's moon, Europa, and Saturn's moon, Enceladus, vast oceans of liquid water lie hidden beneath thick crusts of ice, warmed by the gentle tug of gravity kneading their interiors. We have detected complex organic molecules in the geyser-like plumes shooting out of Enceladus. Could these dark, sunless oceans harbour living organisms, feeding on chemical energy as life does at Earth's deep-sea vents? We have yet to find proof of life beyond Earth, but places like Mars and these ocean moons keep the possibility alive. If life arose independently on even one of them, it would tell us that the spark of life is not unique to our planet, that whenever and wherever the conditions are right, nature may ignite life, even in the far corners of our solar system. Just the prospect of that is profound. It means the universe could be teeming with life, albeit much of it likely simple and microbial, quietly thriving in the nooks and crannies of countless worlds. On the other hand, if after much searching we find that nowhere else harbours even a microbe, that might hint that the leap from chemistry to biology is an exceedingly rare event. Either outcome is deeply significant. Our existence is either one of many or a nearly miraculous singularity. For now, we must live with the uncertainty and continue to explore with curiosity and patience, letting the cosmos reveal its secrets in time. As we ponder the dawn of life on Earth, we also reflect on our own place in this saga. We humans are a product of that ancient turning point. If not for that first living cell, none of us would be here to wonder about it. All of our history, culture, loves and dreams trace back to that unassuming spark in a primeval ocean. It connects us intimately to our planet and to the cosmos at large. The very atoms in our bodies were forged in stars long before Earth existed, and through an incredible sequence of events, they became part of living beings that can now contemplate their own origins. Life's emergence is thus a bridge between the astronomical and the biological, the point where stardust became self-aware. The story of life's origin teaches us a kind of patience and hope. It reminds us that remarkable transformations can occur given enough time and the right conditions. From lifeless chemicals to single cells, from single cells to thinking minds. What an extraordinary progression. Now, here on Earth, one of those minds born of evolution looks back out into space, searching for kinship in the dark. We wonder if somewhere out there, on a planet orbiting a distant star, a similar spark took hold and led to beings who are also looking outward. We know the ingredients for life are widespread across the galaxy. The question is whether the same recipe has played out beyond our world, or whether we are the sole beneficiaries of this cosmic chance. While we have yet to hear a response to that question, we have begun to notice other tantalizing phenomena in the cosmos. They are not messages from another civilization, but they are signals of a sort, brief, intense flashes that for a time defied explanation. With radio telescopes tuned to the sky, we have detected sudden bursts of energy coming from deep space, lasting only milliseconds. These events are known as fast radio bursts, and they are like cosmic flashbulbs, momentary blips of radio waves that appear and vanish in the blink of an eye. For years, they were one of astronomy's great enigmas. What could possibly be causing such powerful, yet fleeting outbursts? In our continuing journey, let us drift now into the mystery of these fast radio bursts, transient sparks in the darkness of the universe, and see what insights they reveal as we sail onward through deep time. High in a quiet valley, a radio telescope listens to the sky. For days and months, it hears the usual cosmic static and the familiar songs of known celestial objects, the steady pulsing of distant pulsars, the whispering hiss of far-off quasars, the crackle of lightning on Jupiter. But one day, something entirely unexpected reaches its ears, a burst of radio waves unlike anything recorded before. It arrives suddenly, lasts only 1,000th of a second, and then is gone. In that fleeting moment, a massive spike of energy hums through the telescope's detectors. Then silence returns. At first, the astronomers are puzzled. Could it have been a glitch? Some terrestrial interference? Perhaps a stray signal from a satellite, or a microwave oven back on Earth? Yet upon careful analysis, they realize this burst came from the sky, far beyond our planet. It was real, and it was extraordinary. This was the first clue of what we now call fast radio bursts. When the discovery was recognized and reported, it set the astrophysics community abuzz. Here was a cosmic phenomenon that appeared to release as much energy in a blink of an eye as our sun emits in days. To produce such a powerful burst of radio waves that could be detected across the vast gulf of space, whatever event caused it must be immensely energetic. And yet, it was over almost as soon as it began, leaving no trace but a faint whisper in the data. For a long while after that first burst, only a handful of these events were found. Each time one was detected, it was singular, occurring once and not repeating, which made them hard to study. They seemed to pop up at random locations on the sky and then vanish, like cosmic fireflies at dusk, winking out before you can catch them. Researchers around the world pointed their radio telescopes to the heavens, hoping to catch more of these tantalizing flashes. Slowly, more were detected. Each new fast radio burst, or FRB as they came to be known, confirmed that this was not a fluke or an instrument error. Nature was indeed producing these strange signals. They were incredibly brief, just milliseconds long, but analysis of their radio waves revealed they often traveled billions of light years to reach us. By measuring how the bursts' frequencies were spread out or delayed, an effect of passing through intergalactic clouds of plasma, scientists could tell that many FRBs came from far outside our galaxy, from the depths of intergalactic space. Think about that. A millisecond burst arriving from perhaps halfway across the universe. The source might be a galaxy billions of light years away, so distant that Earth had not even formed yet when the burst of energy began its journey. Across eons it travelled, through the dark and empty reaches between galaxies, dispersing and fading, until it finally fell upon Earth and made a tiny blip in the data of a waiting telescope. In that moment, across an immense gulf of time and distance, we momentarily touched an event that had happened long, long ago, in a corner of the cosmos we may never otherwise know. The mystery deepened. What could cause such brief yet brilliant emissions? Theorists began to brainstorm. One idea was flare-ups from magnetars, extremely magnetic neutron stars known to produce intense bursts of energy. Magnetars are the dense, city-sized remnants of certain massive star supernovae, with magnetic fields trillions of times stronger than Earth's. They occasionally release enormous flares of X-rays and gamma rays. Could they also unleash bursts of radio waves if their magnetic fields crack or reconfigure in a starquake? It seemed plausible. Others suggested catastrophic one-time events, perhaps the final moment of a star collapsing into a black hole, or the merger of two neutron stars could produce a quick but potent flash of radio energy. There were even more exotic proposals, like colliding black holes or hypothetical cosmic strings snapping in the fabric of space-time. For a time, without much data, speculation ran wild. Some even whimsically mused about alien civilizations. Could FRBs be powerful beacons or lighthouses used by distant intelligences to signal across the galaxy? Most scientists viewed that as highly unlikely, but the mere fact such extraordinary ideas were pondered shows how unexplained these bursts were at first. Clues, however, were slowly accumulating. A breakthrough came when one of these bursts was discovered to repeat. Rather than a one-off firecracker, here was a source that sent out multiple bursts over time. This meant whatever was causing it didn't destroy itself in the process, unlike a cataclysmic collision. Astronomers managed to pinpoint the location of this repeating FRB on the sky and identify the galaxy it came from. A faint dwarf galaxy, billions of light years away. This was a vital clue. The environment of that source seemed to be one where stars were forming rapidly, the kind of place you'd expect to find young neutron stars or magnetars. As more repeating bursts were found, some with irregular patterns, and one even showing a regular 16-day cycle, the magnetar hypothesis gained strength. Then, in a dramatic moment in 2020, our own Milky Way provided a smoking gun. A known magnetar within our galaxy suddenly belched out a short, intense radio burst that, when detected, looked very much like a weaker version of the extragalactic FRBs. It was as if nature handed us a Rosetta Stone. direct evidence that magnetars can indeed produce fast radio bursts. Even with this revelation, not every question was answered. FRBs still hold secrets. We now believe many of them originate from magnetars or similarly exotic neutron stars. But why do some repeat, while others we've only seen once? What exactly triggers each burst on a physical level? Why are a few of them so exceptionally powerful? And are there perhaps different types of FRBs with different origins? The data continue to pour in. New radio arrays scanning wide swaths of sky have detected hundreds of these bursts, revealing that they are not exceedingly rare. In fact, they might be happening all the time across the universe, possibly thousands per day, though only a small fraction are oriented such that their signals sweep past Earth. As we collect more examples, patterns begin to emerge. We've noticed that the bursts can be polarized, indicating they come from areas threaded by intense magnetic fields. Again, consistent with magnetars. Some FRBs also show signs of their signals being distorted or twisted as they pass through magnetic environments, hinting that the source might be in a dense, turbulent region, perhaps near a black hole or within a star-forming nebula. Each burst is like a messenger, carrying not just news of its own existence, but also a record of the journey it took through the cosmos, encoded in its dispersion and polarization. It's poetic to think that in these infinitesimal flashes, we have gained a new tool to probe the universe. A single FRB, by traversing the intergalactic void, can tell us about the matter floating between galaxies. As a burst's waves travel through the sparse plasma of intergalactic space, the lower frequency components are delayed slightly compared to the higher frequencies. This effect, known as dispersion, lets us estimate the density of the wispy gas that lies between us and the source. In this way, FRBs serve as cosmic flashlights, briefly illuminating the otherwise invisible spaces between the stars. With enough FRBs detected from various distances and directions, scientists can begin to map out some of the tenuous structure of the cosmic web, the distribution of gas and plasma stretching between galaxies, much as a few flashes of lightning can reveal the silhouette of a dark landscape on Earth. What began as a puzzling anomaly has evolved into an insightful new field of study. Yet the allure of the unknown still clings to fast radio bursts. We can't predict when or where the next one will occur. We can only be poised to capture it. When a telescope records one, astronomers around the globe leap into action, aiming other instruments, optical telescopes, X-ray observatories, and more, at the spot, hoping for any afterglow or hint of what accompanied the burst. Thus far, FRBs usually leave us with more questions than answers, appearing and fading with no trace of light or energy in other wavelengths. But even in their stark simplicity, they speak volumes. Perhaps most of all, FRBs are a humbling reminder of how much we still have to learn. Not long ago, we had no idea such phenomena even existed. The universe, it turns out, has been peppered with these quick radio flashes for eons, and we only just noticed. It makes one wonder, what other surprises might be out there, flickering beyond our current capabilities, waiting for us to open our eyes a little wider. The story of FRBs, from baffling discovery to partial understanding, embodies the spirit of exploration. The more we learn, the more we realize there is yet to discover. Having listened to the universe's brief, powerful whispers, our gaze now turns to the grander movements in the cosmic ballet. The galaxies that sometimes host these bursts are themselves drifting, bound by gravity's grip. Indeed, our own Milky Way is being gently pulled in a particular direction by a vast, unseen influence. In the cosmic ocean, there are currents and eddies shaped by gravity on the largest scales. One such mysterious flow is drawing us toward a region we cannot clearly see, a region astronomers have ominously named the Great Attractor. Let us follow this gravitational tug now, venturing into the heart of a cosmic mystery hidden behind the bright band of our Milky Way. There is a gentle but inexorable motion carrying our Milky Way galaxy and its neighbours through space. Imagine all the galaxies around us, like a flotilla of cosmic ships, drifting in one particular direction. This motion was first noticed by astronomers decades ago when they measured how galaxies move relative to the uniform expansion of the universe. They expected to see galaxies simply flying apart evenly in all directions, carried by the swell of the Big Bang's expansion. But instead, they found a subtle irregularity. Our Milky Way, along with hundreds of thousands of other galaxies in our vicinity, is moving toward a specific patch of sky at a considerable speed. It's as if an unseen gravitational current is tugging on us, pulling our whole galactic neighborhood towards some unknown shore. The source of this mysterious pull was given a name that captures its essence: the Great Attractor. The name alone evokes a sense of drama, a great cosmic magnet drawing in galaxies. For a time, it almost sounded ominous, as if there was some monstrous object out there that might one day reel us in. In truth, the Great Attractor is not a single object like a black hole or a cosmic vacuum. It's more like a region of space with an exceptionally high concentration of mass, whose combined gravity is perceptibly influencing the motions of galaxies over an immense area, hundreds of millions of light years across. Think of it as a vast, deep valley in the fabric of the universe's gravitational landscape, and our Milky Way is rolling slowly into that valley, along with many others. The speed of our galaxy toward this region is immense by human standards, on the order of several hundred kilometers per second, which is over 2 million kilometers per hour. Yet because of the enormous distances involved, this drift is subtle on human timescales. We won't collide with anything there, or even arrive, for billions of years. It's a journey measured in the age of galaxies, a gentle gravitational nudging rather than a dramatic plunge. One of the intriguing aspects of the Great Attractor is how elusive it is to observe directly. By a cosmic coincidence, the direction in which it lies is heavily obscured by the Milky Way's own disk. When we peer out toward the Great Attractor's location, our view is flooded with the stars, gas, and dust of our own galaxy, a region aptly called the zone of avoidance by astronomers, because it's so difficult to see the distant universe behind it. For a long while, this obscuration was like a veil, hiding whatever lay beyond. Astronomers could infer that something massive was there from the way galaxies around us were moving, but actually seeing what it was made of proved challenging. It was as if we detected the strong tug of an unseen presence, but couldn't make out its shape through the fog of our galactic plane. Over the years, scientists began lifting that veil, using instruments that can peer through dust and stars. Radio telescopes, for instance, detect the faint radio glow of hydrogen in galaxies, which can travel through dust that visible light cannot penetrate. X-ray observatories in space can catch the high-energy shine of hot gas in hidden galaxy clusters behind the Milky Way. Bit by bit, a picture of the Great Attractor's realm emerged. Rather than one ultra-massive object, it appears to be a confluence of galaxy clusters and groups, a busy intersection in the cosmic web. Among these structures, one of the closest and most massive is a cluster of galaxies in the constellation Norma, identified in the 1990s as a major contributor to the gravitational pull. Additionally, astronomers discovered several new clusters and concentrations of galaxies beyond the Norma cluster, each adding to the region's gravitational influence. In one survey, nearly 900 previously hidden galaxies were revealed behind the glare of the Milky Way, each one a swarming city of stars moving in the grand dance toward the Great Attractor's center. The Great Attractor itself is centered roughly 200 to 250 million light-years away from us, in the direction of the constellations Centaurus and Norma. It lies at the heart of an enormous congregation of matter. In fact, our entire local supercluster of galaxies, an immense region of space that includes the Virgo cluster, the collection of galaxies to which our Milky Way belongs, and many other groups, is being steered by gravity in that general direction. Modern studies have delineated this supercluster and given it the beautiful Hawaiian name Laniakea, meaning immeasurable heaven. In this view, the Great Attractor is not so much a singular thing as it is the central gravitational focal point of Laniakea, the basin toward which the galaxies in our cosmic neighborhood flow. And just as rivers ultimately merge into greater streams, beyond the Great Attractor region itself lies an even more massive concentration of galaxies called the Shapley supercluster, which might be extending its influence as well, like a still larger gravity well further downstream. Our Milky Way's journey may be influenced by not just one Great Attractor, but layers of gravitational pull from structures near and far. Despite these advances in understanding, a touch of mystery remains. The distribution of matter we can see, stars, gas, and galaxies, in the Great Attractor region accounts for a lot of the pull, but some measurements hint it might not account for all of it. It's possible that additional hidden mass, perhaps in the form of dark matter, the invisible substance that neither emits nor absorbs light, yet exerts gravity, contributes to the gravitational forces at work in this cosmic locale. So the Great Attractor invites us to consider not just the seen, but the unseen components of the universe. In a way, it's a lesson in humility. Even on vast scales, where we think we have a clear picture, there may be significant pieces missing from the puzzle. What does this great gravitational attractor mean for us here on Earth? In practical terms, very little on human timescales. Our solar system, our planet, and all of us are being carried along with the Milky Way. But the motion is so steady and uniform that it's imperceptible in our daily lives. Much like being on a ship drifting in a slow ocean current, where everything on board feels still and stable. Its importance is more about the insight it gives us into the large-scale structure of the cosmos. Knowing that we are moving toward this region helps us map out the distribution of matter around us on colossal scales. It reminds us that our galaxy, immense and self-contained as it seems, is actually part of a much larger flow of cosmic material, guided by structures far bigger than itself. There is a poetic dimension to this knowledge. Under the night sky, as we gaze at the stars, it all appears calm and unchanging. But in truth, our galaxy is sliding through space, drawn by a faint gravity well millions of light years distant. The great attractor symbolizes that hidden motion. Even when we feel stationary, we are on a grand voyage. Earth orbits the sun orbits the center of the Milky Way, and the Milky Way, along with countless other galaxies, glides toward a point we cannot yet fully see. It's a powerful reminder of the interconnectedness of the universe, how unseen forces link distant galaxies in a common dance. Little by little, the great attractor has yielded its secrets. What began as a perplexing enigma is now an increasingly understood feature of our cosmic landscape. We see it now not as a singular looming thing, but as a densely populated region of the cosmos, a nexus of clusters shaping the movements of galaxies for hundreds of millions of light years around. And as often happens in astronomy, solving one mystery leads to new questions and wonders. The great attractor turned out to be part of an even larger structure, Laniakea and beyond, prompting us to think in still grander terms about the architecture of the universe. Our journey following gravity's pull has taken us into the realm of massive clusters and hidden galaxies. We peered behind the curtain of the Milky Way and glimpsed a grand congregation of galaxies steering our cosmic course. Now, we shift from the tangible to the theoretical, from gravity's observed pull to gravity's potential warps and loopholes. Having followed these cosmic currents, we turn to the idea of cosmic gateways, wormholes and white holes, hypothetical phenomena that stretch our imagination of what space and time might allow. In our quest to understand the cosmos, we sometimes encounter ideas that sound like something out of a dream. Wormholes and white holes are two such concepts. Theoretical oddities predicted by the same equations that give us black holes. They haven't been observed in reality, but they offer a peek at how strange reality might be if nature permits such things. Thinking about them is like stretching the fabric of our imagination. just as they would stretch the fabric of space-time itself. Consider a wormhole first. In simple terms, a wormhole is envisioned as a tunnel or shortcut through space and time. Imagine space as a vast sheet with two distant points marked on it that you'd like to connect. Normally, you'd have to travel across the sheet from one point to the other, a journey that could take eons, even at the speed of light. But if you could fold the sheet so those 2 points touch, then poke a hole so they join, you'd create a shortcut, a wormhole. Through this tunnel, a traveller might step in at one end and emerge at the other almost instantly, even if those two ends are light years apart. It's a captivating idea, a universe with secret back doors that allow one to hop across unimaginable distances in the blink of an eye. The possibility of wormholes comes from Einstein's general theory of relativity, which tells us that space and time can bend, warp, and stretch. Soon after physicists discovered black holes as solutions to Einstein's equations, they realized the equations also allowed for more exotic mathematical solutions. In 1935, Albert Einstein and his colleague Nathan Rosen described what we now call an Einstein-Rosen bridge, essentially a theoretical tunnel connecting two separate points in space-time. This is one way to conceive of a wormhole. In the mathematics, a black hole, an object that pulls things in and doesn't let anything out, could be connected to a sort of mirror image exit, which one might call a white hole, from which things emerge but into which nothing can enter. Together, they would form a kind of tunnel through space and time. The entrance, behaving like a black hole, and the exit, behaving like a white hole, would be the two ends of a wormhole connection. However, just because the equations say something is possible doesn't mean it exists in nature. Wormholes, if they exist at all, might have serious limitations. For one, they appear to be inherently unstable. The natural tendency of a wormhole, according to general relativity, is to pinch off or collapse almost as soon as it forms, effectively closing the door before anything, even a ray of light, can get through. To keep a wormhole open, theoretical physicists speculate that exotic matter with negative energy would be required to hold the tunnel's throat ajar. Negative energy sounds like pure science fiction, but intriguingly, quantum physics does allow for phenomena that involve negative energy densities in small amounts. The Casimir effect, observed in the lab, is one such example. Whether enough negative energy could ever be accumulated or sustained to stabilize a wormhole is a completely open question. At present, it's far beyond anything we know how to do, and it may turn out to be fundamentally impossible. Another concern is that even if a wormhole could somehow be held open, it might not offer a gentle passage. The gravitational tides near the entrance could be extreme. Anything approaching might be stretched or torn by intense forces, much as an object would be spaghettified near the brink of a black hole. And if the wormhole were traversable, and especially if it allowed shortcuts in time, as some solutions suggest might be possible, one confronts the potential for paradoxes. A traveller going through a wormhole and arriving in the past could tangle causality in ways that give philosophers and physicists headaches. The classic grandfather paradox, for instance. These theoretical considerations, while fascinating, serve to remind us that wormholes remain deeply hypothetical. They push the boundaries of physics as we currently understand it, and expose how little we know about reconciling gravity with the other forces in extreme scenarios. Yet, despite all the caveats, wormholes tantalize scientists and dreamers alike. They tap into a fundamental yearning to overcome the vast distances of space. The stars and galaxies are so very far away. Wormholes offer a glimmer of hope, however remote, that perhaps those distances could be cheated. It's no surprise that wormholes appear often in science fiction as convenient portals for interstellar travel. They are the ultimate cosmic subway, enabling grand adventures without the waiting. While fiction takes liberties, science treads carefully. Researchers have even speculated about ways one might detect a naturally occurring wormhole if one existed. For example, by looking for peculiar gravitational lensing effects or unusual motions of stars that might indicate the presence of an invisible tunnel. So far, we haven't found any such signs. If wormholes do exist in our universe, they might be microscopic, forming and vanishing in the quantum foam of space-time. Or perhaps they lurk in exotic configurations we haven't learned to recognize. For now, they remain theoretical constructs. Now, what about white holes? A white hole, as hinted earlier, is essentially the opposite of a black hole. If a black hole is a region of space where matter and light can enter but never escape, a white hole is a region where matter and light can emerge but nothing can enter. It's as if you took a film of a black hole and ran it in reverse. What was an all-consuming pit becomes an outpouring fountain. In theory, if you came across a white hole, you would see matter and radiation spewing out of it, perhaps light and particles streaming outward. But you could never approach the central region or fall in, because space and time would conspire to always push you away. The concept of a white hole comes straight from the mathematics. It wasn't dreamed up as a separate idea, but rather it appears as a possible extension of black hole solutions. When physicists extended the equations that describe a black hole, under certain conditions, a white hole region appears as a mathematical possibility. However, we have never seen a white hole in the cosmos. No astronomer has observed an object that behaves in that stubborn one-way fashion. Black holes, by contrast, are now well-documented astrophysical objects. We infer them by the gravitational pull on their surroundings. We've even imaged the shadow of one with the Event Horizon telescope. But no analogous evidence hints at the existence of white holes. If a sizable white hole were out there, what might it look like? Perhaps from a distance, it could resemble an explosion that never quite dissipates, a continuous or recurring eruption with no clear source. Some speculative thinkers have wondered if certain gamma-ray bursts, those brief, intense flashes of high-energy radiation we see in distant galaxies, could be tiny white holes popping into existence and then expelling their energy in a flash before vanishing. This idea is highly conjectural and not widely accepted, but it's an example of how we might try to imagine a detectable sign of a white hole. Another fanciful notion is that the Big Bang itself was a kind of white hole, a colossal eruption where space, time, and matter all burst outward from an initial singular point. In a sense, the Big Bang did have the one-way character of a white hole. Everything came out, and we still see its afterglow in the cosmic microwave background, with no way to go back beyond that starting singularity. Whether that analogy holds any real meaning is debatable, but it's a thought-provoking connection between the concept of a white hole and the origin of our universe. Wormholes and white holes remain firmly in the realm of theory for now. They serve as reminders that the universe, under the hood of our current equations, has room for very strange possibilities, even if nature doesn't create these phenomena in reality. Just contemplating them expands our sense of what space-time might do under extreme conditions. And who knows? Future generations, with far more advanced technology or deeper understanding, might find ways to test for them, or even, perhaps, create tiny wormholes. There are already speculative ideas in quantum physics. For example, some studies in quantum entanglement and quantum gravity hint at connections that resemble wormholes on a mathematical level. But we are venturing far beyond proven science here. For us, at our current juncture, wormholes and white holes are like cosmic fairy tales, not necessarily false, but fantastical scenarios that spark our wonder. What they do accomplish, at least in our musings, is to bridge our thinking from the concrete to the cosmic. They make us ask very big questions. Can we truly imagine traveling to other galaxies, despite the distance? Are there other universes beyond our own, perhaps connected by hidden corridors, or birthed from the same cosmic fabric? Could something ever escape the confines of a black hole in a way we haven't yet observed? Perhaps through a white hole outlet? These questions naturally lead us to the ultimate beyond question. What lies beyond everything we can see? After all, wormholes toy with the idea of going beyond the normal confines of space and time. So now, setting aside these speculative portals, we turn to a grand mystery that is very much real and immediate: the edge of the observable universe. We all live inside a visible bubble of space and time, bounded by how far light has travelled since the universe began. What lies beyond that horizon? As we sail further on our journey, let's cast our eyes to the cosmos's farthest shores, to ponder the nature of the cosmic horizon, and what, if anything, might lie beyond the universe we know. To find the edge of the universe, we must first understand that, in a sense, we are confined inside a horizon, like sailors on a vast cosmic sea. We peer out as far as we can, but there comes a limit beyond which we cannot see, not because of a wall or barrier, but because of time and the finite speed of light. The universe is about 13.8 billion years old, which means light has had 13.8 billion years to travel. In that time, space itself has expanded tremendously. The farthest light we can currently detect comes from regions that are now much farther away than 13.8 billion light years due to that expansion. In fact, the observable universe, the portion we can see or have a chance to interact with, extends about 46 billion light years in every direction from us. This defines our cosmic horizon. It's as though we are at the center of a sphere of light with a radius of 46 billion light years. Beyond that sphere lies, we don't exactly know what, because no light or signal from those realms has reached us yet. It's important to realize that this horizon is not a physical boundary. It's a limit of vision. Just as a ship at sea cannot see beyond Earth's curvature, we cannot see beyond the curvature imposed by the universe's finite age and the speed of light. If we could magically travel faster than light and leap beyond that horizon, we would presumably find more universe, more galaxies, more space, perhaps much like the region we see around us. Those distant parts of the cosmos are not fundamentally different. They're made of the same types of atoms and obey the same physics. They're just too far away for their light ever to have reached us so far. In all likelihood, the universe extends far beyond our observable bubble. It could even be infinite in extent, or it might curve back on itself in a way that's difficult to visualize. But as far as our best observations can tell, space is extremely flat on large scales and shows no hint of stopping or looping back within the distances we can see. This suggests that if the universe does wrap around or have some edge, that edge lies beyond the observable part. When we gaze out to our horizon, what exactly are we seeing? The most distant visible feature in space is the cosmic microwave background radiation, the faint afterglow of the Big Bang. This light comes from a time about 380,000 years after the universe began, when the hot, dense plasma filling all of space finally cooled enough to become transparent. Before that epoch, the universe was like a foggy fireball, so hot and full of charged particles that photons, particles of light, couldn't travel far without bouncing off something. At about 380,000 years, that fog cleared. Atoms formed, space became transparent, and light was free to stream across the cosmos. That light has been traveling ever since, stretching to microwave wavelengths as the universe expanded, and it now forms a nearly uniform glow that we detect in every direction. It appears to us as a faint, cool temperature background, just a few degrees above absolute zero. When we look at it, we're effectively seeing a wall of light from the edge of the observable universe in time. The oldest light we can see. It's not a wall in space, but a horizon in time. We cannot see further back because earlier than that, the universe wasn't transparent to light. We might someday detect neutrinos or gravitational waves from earlier eras, which would let us peer back closer to the Big Bang. But with light, the cosmic microwave background is the limit of our sight. So what lies beyond our observable universe? The honest answer is, we don't know for sure, because we cannot observe it. But our best guess, founded on what we know of physics and cosmology, is that there's simply more universe out there. If the cosmos is infinite, then beyond our horizon, there are infinitely more stars and galaxies, perhaps even planets and life, just too far for us ever to know. If the cosmos is finite but unbounded, like how the 2D surface of a sphere is finite in area but has no edge, then if you travelled far enough in one direction, you might eventually end up back near where you started. Although in practice, the universe might be so huge that that journey is effectively impossible with any foreseeable technology. In either case, there's no indication of any abrupt boundary where physics changes or emptiness begins. The universe likely continues with the same grand tapestry beyond what we can see. This idea can be hard to wrap our minds around. Humans are used to edges and borders. Every lake has a shore. Every land has its coastline. But space doesn't necessarily work that way. If space is infinite, it has no edge. If it is curved and finite, it still has no edge in the sense of a boundary. It could be analogous to the surface of a globe, where you can keep going around and around. When we ask, what is outside the universe? It might be a trick question, because if the universe is truly everything there is, space and time themselves, there is no outside. If instead we define universe as just our observable part, then outside that is simply the rest of space we can't see. Our inability to see beyond the horizon doesn't stop us from wondering. Cosmologists think that our observable patch is probably very typical, and that on much larger scales, the universe, on average, looks the same everywhere. This is called the cosmological principle. There's no preferred center or edge. If that's true, then beyond our horizon are galaxies and more galaxies, perhaps with their own curious inhabitants, asking the same question in reverse. What lies beyond their horizon, which would include us, though they can't see us either? It's a profound thought that the limit we have is reciprocal. We are someone else's beyond the horizon. There's also the possibility that beyond the observable universe might include exotic things we haven't imagined. But again, we have no evidence of that. Some speculative theories suggest that if space goes on forever, every possible arrangement of matter will occur somewhere. That means far beyond our view, there could be regions of the universe drastically different from ours, simply by chance. Different distributions of galaxies, maybe even physics that unfolded differently if those regions are so far that they're essentially separate from ours since the early universe. Pushing further, some theories of cosmic inflation, the idea that the early universe underwent a tremendous expansion, suggest that our universe might be just one bubble in a frothy sea of bubble universes, a multiverse where each bubble is a separate universe with potentially different properties. If that is the case, then beyond the universe might mean beyond our bubble, where entirely different universes exist, forever unreachable and unseen, born from the same cosmic process that gave rise to ours. These ideas are highly speculative and currently untestable, so they remain in the realm of philosophical musing. Still, it's amazing that by thinking about what lies beyond our horizon, we're led to contemplate not just a bigger universe, but perhaps a grand multiverse of many universes. Bringing our thoughts back to what we do know. As of now, we see an observable universe filled with structure, clusters and filaments of galaxies, great voids, a web-like arrangement of matter that extends to the limits of our vision. There's nothing to suggest that web stops at the edge of what we can see. It likely continues. The cosmic horizon is more a reminder of our limitations than a limit of the cosmos. It's the ultimate boundary of what we can observe, and it quietly tells us that no matter how hard we try, some things will remain beyond our reach. There will always be a frontier just a bit further out. Standing, as it were, at the cosmic shoreline, we experience a mixture of understanding and mystery. We understand quite well why we have a horizon and roughly how large it is. We have even measured that the universe's expansion is accelerating, which means our horizon defines a region that will only shrink in terms of accessible galaxies over trillions of years. That adds a touch of poignancy. The universe we see now is, in part, a temporary gift. Galaxies at the edge of our view are already slipping away due to expansion. Eventually, their light will never reach us. But on human timescales, and even civilizational timescales, the stars we see in our telescopes today will continue to shine for us. The horizon is not something that changes overnight. Contemplating the edge of the universe often brings a sense of calm and inevitability. There are limits to what we can know, and that's all right. It makes the universe feel even grander and more mysterious. We started by asking if we are alone, and ended up considering the possibility of infinite realms beyond our sight. Each step of this journey has enlarged our perspective and instilled a gentle awe. As our journey through these cosmic mysteries draws to a gentle pause, we are left with a serene sense of scale. We began beneath the stars, wondering about life in the cosmos, and we travelled through the saga of life's beginnings, the flickers of mysterious signals from deep space, the pull of an unseen gravity, and the theoretical gateways of space-time, arriving finally at the vast horizon encircling all we can see. Now, contemplating that cosmic horizon, we sense both the grandiosity of what we know and the inevitability of the unknown beyond. But this is not an end. The universe extends beyond the horizon, and time flows ever forward. So too does our journey. In the grand flow of cosmic time, this stage of our exploration comes to a resting point, not a conclusion. We drift here, at the edge of what's observable, letting our thoughts sail onward into the unknown. The story of the cosmos continues, and we remain ever curious travellers, gazing into the endless night, stars above, questions ahead, gently carried by the currents of deep time toward the next mysteries, awaiting just beyond that cosmic horizon. In the stillness of cosmic night, we continue our gentle voyage. The journey thus far has left us marvelling at the tapestry of the cosmos, and now we wonder what deeper truths lie beyond the horizon of understanding. Softly and without pause, we drift onward, carried by curiosity into the next expanse of exploration. a profound question glimmers ahead in the darkness. A question of unity, a search for the hidden foundations of reality. In this quiet moment, our thoughts turn toward that mysterious beckoning light, the possibility that everything we have ever known might be connected by a single, elegant truth. Physicists sometimes speak of a theory of everything, not a figurative phrase, but a literal goal, a single framework that would unify all the forces and particles of nature into one comprehensible whole. Imagine, for a moment, that the sprawling complexity of the universe could be distilled down to an equation written on a chalkboard, or a principle whispered in the language of mathematics. It would be as if all the chapters of nature's story, gravity, light, energy, time, were pages bound together in one grand book. The idea promises a kind of cosmic simplicity, a unity behind the diversity of phenomena we see around us. This yearning for unity is not new. In the history of science, we find a pattern, the unification of ideas that once seemed separate. Long ago, Isaac Newton realized that the force pulling an apple to the ground was the same force guiding the moon in its orbit around Earth. In that revelation, the sky and the ground were unified by gravity, binding the heavens and earth as one. Centuries later, James Clerk Maxwell discovered that the dancing spark of electricity and the invisible waves of magnetism are threads of the same woven cloth. Electricity and magnetism unified into electromagnetism. Step by step, science has been stitching together the tapestry of physical laws, finding common themes where once there seemed only fragments. By the late 20th century, scientists had taken another step on this path to unity. They found that two of nature's fundamental forces, electromagnetism and the weak nuclear force, which governs certain types of radioactive decay, are actually different facets of one underlying force. Under conditions of extreme energy, as in the young universe moments after the Big Bang, these forces merge into what physicists call the electro-weak force. It was a hint that deep down, the universe might be simpler than it appears. The forces we observe now, having split off from a primordial unified force as the cosmos cooled and expanded. Emboldened by these successes, physicists dared to imagine the next steps, a grand unification that would bring the strong nuclear force, the glue holding atomic nuclei together, into the fold with the electroweak, and ultimately the most elusive unification of all, to include gravity itself. Gravity has stood apart, described by Einstein's elegant general theory of relativity as the curvature of space-time, while the other forces are described by quantum mechanics as particle exchanges in a flat space-time. Reconciling these views is no simple task. It is as if two languages, relativity's geometry and quantum theory's probabilities, must be translated into one another. Yet the dream persists. Somewhere, perhaps, there is a theory that speaks both languages, uniting the realm of the very large with the realm of the very small. Albert Einstein himself spent the last decades of his life chasing this very dream. He felt deep in his soul that nature's laws should harmonize, gravity and electromagnetism joining in a single framework. Though he never found the final key, his relentless search inspired generations. Today, teams of scientists around the world carry on this quest. They have proposed bold ideas, mathematical models that reach toward a theory of everything. Some of these ideas suggest that if we peer far enough into the fabric of existence, we might find something unexpected, additional dimensions of space hidden from view that could be the secret chambers where the forces of nature merge into one. It's a strange thought. Dimensions of space beyond the three we move through in daily life. We live in a world of length, width, and height. Up, down, left, right, forward, backward. These directions define everything we can touch or see. But what if there is another direction, a hidden dimension curled up somewhere, so tiny or so remote that we never notice it? What would it mean to have space extend in ways we cannot point to? To imagine this, let's begin with a simple analogy in a flatter world. Imagine a world that is perfectly flat, like a sheet of paper inhabited by tiny flat creatures. They have length and width to move around in, but no concept of height. One of these flat beings scurries about, unaware that a third dimension, upward, exists. Now picture a sphere passing through this flat land. To the flat creatures, the sphere's intersection with their plane would appear as a shape that changes size. First a small circle, then a larger circle, then smaller again, mystifying those little beings. They would have no idea that what they're really seeing is a three-dimensional object, glimpsed in two-dimensional cross-sections. In their limited view, a sphere is unimaginable, just as a fourth spatial dimension is hard for us to imagine. We, in our three-dimensional world, might similarly be seeing only slices of a higher dimensional reality without realizing it. The notion of unseen dimensions began as a curious speculation. Over 100 years ago, some scientists wondered if our four-dimensional space-time, three of space and one of time, might not be all there is. One mathematician proposed that if a tiny extra spatial dimension existed, it could unify gravity and electromagnetism in one mathematical framework. In his equations, that hidden fifth dimension seemed to provide the extra room needed to link those forces. It was an astonishing, if odd, idea, largely set aside at the time because no one could see this extra dimension or prove it was real. Decades later, the idea resurfaced with new urgency in the form of string theory. This bold theory suggests that all fundamental particles and forces are manifestations of unimaginably tiny, vibrating strings of energy. But for the mathematics of string theory to work, astonishingly, it requires extra dimensions of space beyond the three we know. Not just one extra dimension, but several. String theory typically envisions 10 or even 11 dimensions in total. Where could all these dimensions be hiding? The answer is that they might be curled up so small that we never notice them. Or perhaps we are confined to a three-dimensional surface within a higher dimensional space, like a soap bubble floating in a vast invisible ocean. To picture a hidden dimension curled up on itself, imagine looking at a long garden hose from far away. It might appear as a simple line, one-dimensional, but up close you'd see its round shape. An ant crawling on the hose's surface could go not only along the length, but also around the circumference. That circular direction was invisible from a distance. Likewise, the extra dimensions of space could be like tiny circles, or more complex shapes, at every point in our familiar space. We don't see them because they are microscopically small, rolled up on themselves. Only at extremely high energies or on tiny scales might those hidden directions reveal their presence. Another way to hide dimensions is to imagine that we are stuck on a kind of membrane, a three-dimensional surface, floating within a larger cosmos that has more dimensions. All the particles we know might be confined to this membrane, unable to move in the other directions, much like a drawing on a sheet of paper is restricted to its 2 dimensions. Meanwhile, gravity, which is a warping of space itself, might spread out into the wider dimensional space. This could explain why gravity is so much weaker than the other forces. We feel only a fraction of it, the rest leaking away into those unseen spaces. It's a mind-bending idea that our whole universe might be like a small raft afloat in a grander, invisible reality. How would we ever know if hidden dimensions are real? Scientists have thought of ingenious ways. One idea is to look for subtle changes in gravity's behavior at very small scales. If gravity seeps into other dimensions, it might become stronger than expected at tiny distances. Another approach has been to search for microscopic black holes in high-energy particle collisions. If extra dimensions exist, the energy required to create such mini black holes might be lower than in a 3-dimensional space. So far, these tests have not revealed anything definitive. The extra dimensions remain elusive, neither confirmed nor ruled out, lurking in the shadows, if they exist at all. Whether or not these hidden dimensions are real, they offer a profound lesson. The universe might hold more than meets the eye. Just as our ancestors had no inkling of galaxies beyond the Milky Way, or of the quantum dance within an atom, we too might be unaware of entire aspects of reality around us. It is a humble kind of wonder to think that right here, in the space we occupy, there could be additional directions unfurling beyond perception. The idea stretches our imagination, inviting us to step beyond the comfort of the known and into a broader cosmic perspective. In the hush of the night, as we contemplate these hidden corridors of existence, we feel the veil between the seen and unseen grow just a little thinner. While such theoretical realms hint at unseen possibilities, the universe we do see presents its own profound mystery. We notice that the cosmos, as vast and varied as it is, operates within a narrow band of conditions that just happen to allow stars to shine, planets to coalesce, and life, like us, to emerge. It's as if the universe is balanced on a knife's edge, with fundamental settings tuned precisely right. Too much here, too little there, and the cosmic story could have been very different, perhaps lifeless, or at least unrecognizable. This realization is often called the fine-tuning of the universe, and it paints a picture of a Goldilocks cosmos, not too hot or too cold, not too dense or too empty, but just right for complexity and life to flourish. To appreciate how delicate this balance is, imagine the universe as a cosmic recipe. Each fundamental constant of nature is like an ingredient measured with astonishing precision. Take gravity, for example, the gentle force that governs the dance of planets and stars. If gravity were only slightly stronger, the universe might have pulled itself back together soon after the Big Bang, collapsing in on itself before galaxies could form. Stars, if they ignited at all, would burn through their fuel much faster, living short, intense lives with no time for planets to develop around them. On the other hand, if gravity were a touch weaker, everything would drift apart too easily. Galaxies might never coalesce, stars might never kindle. The cosmos would be a thin, cold mist with nowhere for life to take root. Consider also the strong nuclear force, the glue within atomic nuclei. It's incredibly potent at tiny distances, binding protons and neutrons together. If this force were just a few % weaker, atomic nuclei would be fragile. Many of the elements essential for complex chemistry would never form. The universe might be left with only the simplest element, hydrogen. Without heavier elements like carbon or oxygen, there would be no rocky planets, no water, and no biology as we know it. But if the strong force were slightly stronger, it would bind nuclei too aggressively. Hydrogen, the lightest element which plays a crucial role in star formation and as a component of water, might be rare or non-existent, as it would fuse into heavier elements too readily. In either case, the chemistry of life would be fundamentally stunted from the start. Even the electromagnetic force, the force that binds electrons to atoms and makes chemistry possible, must be just so. If the electric charge of the electron were different, or if the force holding electrons around nuclei were a bit stronger or weaker, atoms might not form stable structures, or the rich chemistry that underpins biology could be impossible. And consider the strange entity known as dark energy, a kind of subtle pressure woven into the fabric of space that is causing the expansion of the universe to accelerate. The amount of dark energy in our universe is incredibly small, yet not zero. If it were much larger, the universe might have expanded too swiftly for galaxies to gather and stars to light. If it were negative, acting to pull things together rather than push them apart, the cosmos might have recollapsed long ago in a premature big crunch before life had a chance to evolve. Somehow, dark energy sits at a value low enough to let structures form over billions of years, yet gentle enough only to dominate the expansion on the very largest scales after those structures have taken hold. It's not just one or two coincidences. There are numerous such parameters, a handful of numbers etched into nature, that define our reality. They include the strengths of forces, the masses of fundamental particles, and initial conditions, like the density of the universe. Each one appears carefully set within a range that permits complexity. Tweak any of them ever so slightly, and the house of cards that is our universe could collapse into a barren or chaotic state. It's as if we have won a cosmic lottery. Out of an unimaginable space of possibilities, we got a ticket that allowed a rich, evolving universe and the emergence of life. Why is the universe so finely tuned? It's a question that stretches beyond science into philosophy and even theology. Some say we simply got very lucky, that out of countless possible universes, we inhabit the rare one where everything happened to work out. And of course, we observe it, because only in such a universe could observers like us arise. This reasoning is known as the anthropic principle. We see the universe the way it is, in part because only a universe compatible with our existence could ever be observed by us. Others suspect there is a deeper principle at play, that perhaps future physics will show these constants are not random at all. Maybe there is some underlying law or logical necessity that fixes their values, so that, in the end, the universe had to be the way it is, and the apparent fine-tuning is just an illusion born of our incomplete understanding. Then there are those who find in fine-tuning a hint of purpose. They argue it's evidence of a cosmic design, that perhaps an intelligence, a cosmic designer of sorts, set the dials of reality just right, so that life and consciousness could eventually blossom. This interpretation ventures beyond what science can test and enters the realm of metaphysics or faith. It brings comfort to some and skepticism to others. Science, by its nature, doesn't assume purpose. It looks for mechanisms, and one very different mechanism has been proposed to explain fine-tuning without invoking sheer luck or deliberate design. The idea that our universe might be just one of many, part of a grand multiverse, where a vast ensemble of universes exists with varied properties. In such a scenario, it's no surprise that at least one universe has the just right conditions, because with enough tries, even the rarest lottery numbers will come up. We might just happen to live in that rare universe, simply because it's one of the few where conscious beings like us can exist to marvel at it. This idea that our universe could be one of many is where our journey now leads. Imagine, for a moment, that the entirety of our known cosmos, all the galaxies stretching out in every direction, all the stars and nebulae, the background afterglow of the Big Bang, even the hidden dimensions and finely tuned constants. Imagine that all of this is just one small part of a much larger reality. The concept of the multiverse invites us to picture an endless expanse beyond our own universe, an ocean of universes where ours is but a single sparkling bubble. In this vast cosmic ocean, there could be countless other bubbles, other universes, each perhaps with different laws of physics, different histories, maybe even additional dimensions or forms of matter and life. It's a staggering idea. What we once assumed was everything might instead be just one island in an unimaginably vast archipelago of realities. One potential way such a multiverse might arise comes from our understanding of the very beginning of our universe. According to the theory of cosmic inflation, in the first fraction of a second after the Big Bang, space itself expanded at an absolutely mind-boggling rate, far faster than the speed of light, since it was space itself stretching. Our entire observable universe grew from a microscopic seed to astronomical size in the blink of an eye. But inflation might not have been a one-time, everywhere event. In some regions of the greater cosmos, inflation could have stopped, like in our patch, allowing galaxies and stars to form, while elsewhere it continued unchecked, stretching space ever bigger and creating essentially separate bubble universes that became disconnected from each other. In this eternal inflation scenario, new universes are continually budding off like bubbles in a foam. Each bubble may go through its own big bang, develop its own mix of particles and forces, and evolve independently. Our universe would be just one bubble that happened to slow down its inflation and cool into matter and galaxies. If we picture this, we see our cosmos as a little bright sphere drifting in an endless, inflating sea, surrounded by other spheres that we can never reach or see, because the space between us is still inflating, pushing them away. The multiverse idea also pops up when we look at the very small, at the peculiar world of quantum physics. In that realm, events don't have single, definite outcomes the way we're used to in everyday life. Instead, particles exist in a blurry superposition of possibilities until they interact with something or someone observing them, at which point we see a definite outcome. One interpretation of quantum physics, called the many worlds interpretation, suggests that all possible outcomes actually happen, each in its own separate branch of reality. If a radioactive atom could either decay or not decay in a given time, then in one branch it decays, creating one timeline, and in another branch it does not, creating a parallel timeline. This would mean the universe splits into copies of itself for every quantum event. Essentially, a constantly branching multiverse of parallel worlds. In some of those worlds, maybe I'm saying something slightly different right now, or you're sitting in a different room, or wearing a different shirt. Most differences would be trivial at first, but over time, they could compound. In other worlds, perhaps larger historical differences have occurred. Alternate histories where events turned out another way. According to this interpretation, these parallel universes all exist just as concretely as our own, but they are non-communicating once they diverge. We can't jump from one branch to another any more than we can hop into a different bubble universe of the inflationary multiverse. They're like shadows cast in different directions, each real in its own frame, but invisible to the others. Even our attempts at a theory of everything had an unexpected brush with the multiverse. String theory, in trying to unify physics, found that it doesn't have one unique solution, but a vast number. The equations allow for a huge variety of ways to shape the extra dimensions and assign values to physical constants. This multitude of possible self-consistent universes is sometimes called the string theory landscape, a landscape of possible universes, each with different laws. Our universe would correspond to one point in that landscape, but there could be many other points representing other logically possible universes. Some physicists have speculated that maybe all those possibilities actually exist somewhere, that the landscape is realized as a multiverse. In that picture, the job of fundamental physics shifts a bit. Instead of explaining why our constants have the values they do in a unique way, it might say, there are countless universes with all different values, and we find ourselves in one that has the kind of physics that allows observers to exist. Now, the multiverse, whether arising from inflation, quantum branching, string theory, or other ideas, is a bold and speculative concept. By definition, if these other universes are truly separate, we might never get direct evidence of them. It's a bit like a fish trying to prove the existence of other ponds beyond its own. If it can't ever leave its pond, it must infer the others indirectly, if at all. Some scientists argue that, without observable evidence, the multiverse idea is more philosophy than science. Others argue that the multiverse is a natural prediction of certain theories we can test, like inflation or quantum mechanics, and thus, indirectly, if those theories hold up, they lend credence to the multiverse. Attempts have been made to find hints. Some cosmologists have even searched the cosmic microwave background, the faint afterglow of the Big Bang, for unusual patterns, like circular dents or temperature anomalies, that might indicate our bubble universe once collided with another in the distant past. So far, nothing conclusive has been found. Whether or not a multiverse is real, thinking about it expands our perspective dramatically. It challenges the notion that universe means everything that exists, and instead suggests a perhaps infinite collection of every possible existence. It's a humbling thought, much like when people first realized that Earth is not the center of the solar system, or that our galaxy is just one among billions. At each of those steps, our cosmic importance seemed to shrink, yet our understanding grew. If our universe is one of many, it means the story is bigger than we thought. It might make our personal and collective existence feel even more precious in its particularity. Out of all those universes, this is the one we experience. This is the one where we are alive. And it might also make us wonder about brothers and sisters out there in other universes, minds that we can't reach, but that we can imagine. Some perhaps fundamentally different, others strangely similar. For all the grand speculation about multiple universes, we remain rooted in our own. This is the universe we know and love, the one where our story is unfolding. And that brings us to a profound and poignant question. What will ultimately become of it? We've looked back to the beginning of time. Now, we peer ahead to the very end. What is the fate of our universe? Will time itself someday stop, or transform, or loop around? In the final leg of our voyage, we explore the possible endings of the cosmos, the end of time. Time flows ever forward, at least in our everyday experience. And as it does, the universe evolves, gazing far into the future, far beyond any human timescale. We can imagine how the cosmos might change, and eventually meet its destiny. In the silence of deep time, trillions upon trillions of years from now, the stars themselves will tell the final chapters of the cosmic story. In those distant epochs, the night sky will not be as we know it today. Over immense spans of time, the stars that grace our heavens will age and die. The most massive stars live fast and perish young, exploding as supernovas and leaving behind remnants like neutron stars or black holes. More modest stars like our Sun will shed their outer layers, forming beautiful planetary nebulae for a brief time, and then end up as white dwarfs, small, dense embers that slowly cool in the dark. Crucially, the raw material for making new stars, vast clouds of gas and dust, will become scarce. Much of it will have been incorporated into stars and locked in remnant objects, or blown out of galaxies, or sucked into black holes. The cosmic gas tank will run low. As the existing stars burn out, fewer new ones will take their place. The universe, so brilliant in its youth and middle age, will gradually lose its luster. Picture a time, perhaps 100 trillion years from now. By then, the formation of new stars will have essentially ceased. The great galactic cities of stars will grow quiet as their inhabitants wink out one by one. The last shining stars, perhaps red dwarfs that burn their fuel so slowly they can live trillions of years, will finally exhaust their hydrogen. They will fade to black, becoming cold remnants like black dwarfs, cooled white dwarfs that are dark, of which none yet exist, since the universe isn't old enough. The galaxies, once ablaze with billions of points of light, will be dark silhouettes against the dim backdrop of space. Only objects that don't shine by their own light will remain. Black holes, cold stellar remnants, lone planets, and diffuse atoms spread thin. Yet even in this darkness, subtle activity continues. White dwarfs might occasionally collide and merge, potentially creating a new brief burst of fusion, a reborn star, or a supernova flash in the dark, breaking the monotony for a moment. Brown dwarfs, failed stars, or free-floating planets might collide and spark faint new heat, but these events grow increasingly rare. As the universe expands, galaxies that are not gravitationally bound to each other recede beyond each other's horizons, meaning, over very long times, each remaining clump, like our local group, which will by then have merged into one big elliptical galaxy or been eaten by black holes, will be essentially alone, island universes in a vast void. On these timescales, even black holes, those seemingly eternal abysses, are not forever. Stephen Hawking theorized that black holes slowly evaporate by emitting Hawking radiation, an almost negligible trickle of particles from just outside their event horizons. For stellar mass black holes, the evaporation time is colossal. around 1067 years, a 1 followed by 67 zeros. Compare that to the current age of the universe. 10 years. For the supermassive black holes in galactic centers, the lifetimes are even more enormous, on the order of 100 years or more. But given enough time, even these giants will evaporate completely, ending in a final burst of gamma rays and particles as they disappear. So, imagine that far future when the last black hole has radiated away. We're talking timescales that defy true comprehension. What remains in the universe at that point? Almost nothing organized. A few stray elementary particles, maybe some positrons and electrons, neutrinos, drifting through a vast volume of essentially empty space. The temperature of the universe will be infinitesimally above absolute zero, as close to perfect cold as physics allows, because all sources of heat, stars, collisions, even black hole emissions, are gone. This scenario is often referred to as the heat death or big freeze of the universe, a state of maximum entropy where all the energy that once drove stars and life is spread thin and uniform, no longer able to do work or create interesting structures. In that final darkness, the arrow of time, which is so tied to the increase of entropy and the occurrence of events, would effectively lose its meaning. Nothing happens from one eon to the next, for there are no clocks ticking, no processes unfolding. Time would stretch out, but with no change to mark it, it's almost as though time has ceased. The universe, quiet, cold, and desolate, simply is. This is a melancholic vision, to be sure. The death of the universe as a whimper, an eternal fading to black. But before that darkness, there could be other more dramatic finales, depending on the deeper properties of our cosmos. One alternative end scenario is the Big Rip. This depends on the nature of dark energy, the mysterious force accelerating the expansion of space. If dark energy is not constant, but instead grows stronger over time, a form sometimes called phantom energy, it could lead to a runaway expansion. In such a case, billions of years from now, the repulsive effect of dark energy would increase to the point that it overcomes all other forces. First, distant galaxies would be carried away so fast that their light can no longer reach us. Next, the expansion's pull would loosen the gravity binding galaxies, tearing them apart. Later, it would overwhelm the gravity, holding solar systems intact. Planets would fly off from their stars. In the final minutes or seconds before the end, even the atoms themselves could be ripped apart as the fabric of space accelerates without bound. Ultimately, every particle would be isolated, rushing away from every other. The universe would literally rip itself apart in a final, catastrophic expansion. The Big Rip, if it were to occur, would put a hard, finite limit on the lifetime of the cosmos, perhaps tens of billions of years from now. Current observations of dark energy, which so far behaves like a constant called the cosmological constant, don't show signs of this phantom behavior, so the Big Rip is not considered likely by most physicists at the moment, but it's a conceivable fate if our understanding of dark energy changes.
Another possibility is the opposite of a bang, a big crunch. If the density of matter, or a change in dark energy, were high enough to someday halt and reverse the expansion, then the universe could stop expanding and begin to contract. Over an immense time, galaxies would draw closer together. Distant galaxies that had disappeared over the horizon would come back into view as space shrinks. The night sky would grow brighter again as everything crowds closer. Galaxies might collide and merge at an even greater rate. The temperature of the background radiation would climb from near absolute zero back up as compression heats the universe. Eventually, all matter might crunch back into a hot, dense state. Perhaps even a singularity, not unlike the initial Big Bang, closing the cosmic loop. Some speculative models suggest this could then rebound in a new Big Bang, a cyclic or oscillatory universe scenario, where each universe is born from the death of a previous one, in an eternal series of breaths, in and out. However, given what we see, particularly dark energy's push, the Big Crunch is not in favor for our universe, but it remains a haunting, symmetrical end in theory. Fire to fire, ashes to ashes, a cosmic phoenix.
Whichever way the universe might end, these are timescales and energies far beyond human comprehension. They make our present era seem incredibly vital and warm, like living in the spring of the cosmos, knowing that winter, however far away, is ultimately coming. It's worth noting that if the heat death scenario is correct, we live at a very special time in the universe's life, when it's old enough for complexity to have emerged, but still early enough that stars shine and galaxies thrive. In the extremely far future, it would be a rather lonely, cold existence indeed. Reflecting on these cosmic ends can evoke a sense of existential smallness, or even sadness. But there's another way to look at it. The fact that we can understand and imagine these futures is itself a triumph of consciousness. We are, as far as we know, the first beings on Earth, and maybe in the galaxy, to project our minds billions of years forward and backward, to envision the birth and death of universes. It's a profound expansion of our perspective, and it can cast a gentle, philosophical light on our everyday concerns. Everything we know and experience is part of a larger cosmic story, a story with a beginning and apparently with an end. Yet, that ultimate end is so distant that it need not trouble us like an immediate worry. In a practical sense, For countless generations to come, the stars will continue to shine. New stars will be born. Galaxies will swirl. Life, here or elsewhere, will have the potential to thrive. Our own sun still has about 5 billion years before it exhausts its fuel, an almost absurdly long time relative to human history. And even after the sun is gone, the galaxy will continue on. The universe is young compared to its eventual lifespan in these scenarios. So, while we acknowledge the end in theory, we also celebrate the enormity of time between now and then. Now, having ventured to the end of time, we find ourselves gently drifting back to the present, as if we've zoomed out to the furthest future, and now let the pendulum swing back to the here and now. It is still night around us, presumably, if you're listening in the intended setting. The stars we see tonight are in their midlife glory. The universe is bustling and very much alive. We have travelled from the birth of the universe to its possible death and returned with a kind of quiet wisdom that everything changes and that even great things have chapters of birth, life, and conclusion. After journeying so far outward in space and so far forward in time, a different kind of question arises, one that turns our gaze inward. What is all this? We've been talking about the universe as the ultimate reality, but some have dared to ask whether the universe itself might be an elaborate illusion of sorts. In the final part of our journey, let us gently step back from the physical cosmos and question the nature of reality. Could it be that our entire cosmic experience, everything we see, feel, and are, is taking place within some sort of grand simulation or dream? In the quiet of this moment, such an idea finds space to unfold without shock, just curiosity. Is reality an illusion? Could the universe be a simulation? The notion that reality might be an illusion is not new. It's an ancient and recurring theme in philosophy and mythology. Plato's allegory of the cave comes to mind. Prisoners in a cave see only shadows on a wall and take them for the whole of reality, unaware of the real objects and fire casting those shadows behind them. Many spiritual traditions have similar concepts. In Hindu philosophy, the term Maya refers to the illusory nature of the world, suggesting that the reality we perceive is like a veil, and a deeper, truer reality lies beyond. René Descartes, the French philosopher, famously considered that all his sensory experience could be a deception by an evil demon, and he resolved to doubt everything until he found an indubitable truth. I think, therefore I am, was his answer to that conundrum. These ideas prepared the ground for what today we call the simulation hypothesis, the proposal that perhaps our universe is an artificial simulation, like a cosmic scale computer program created by some advanced intelligence. It sounds like science fiction, and indeed it has been the subject of films and stories. But some scientists, philosophers, and futurists take the idea seriously enough to discuss its likelihood. One of the most cited arguments comes from philosopher Nick Bostrom. In simple terms, Bostrom argued that at least one of the following statements must be true. 1. Almost no civilization reaches a level of technology where it can run realistic ancestor simulations. They either go extinct first, or it's just physically impossible to do. 2. If civilizations do reach that advanced stage, none of them choose to run a significant number of simulations of their past, perhaps due to ethical reasons or lack of interest. 3. If neither 1 nor 2 is the case, and advanced civilizations run many simulations, then the number of simulated conscious beings would far exceed the number of original beings, and therefore, statistically, we would most likely be among the simulated ones rather than the originals. In other words, if one day people, or aliens, can create billions of simulated universes, the odds that we happen to live in the single real universe versus one of the billions of simulations would be astronomically small. This line of reasoning leads to the startling possibility that we are indeed living in a simulation right now. Some high-profile individuals and scientists have echoed aspects of this argument, musing that the chances we're in base reality might be, say, only 1 in billions. It is, of course, a hypothesis, one that is very hard to test. How would one know if they're in a simulation? If the simulation is done perfectly, you wouldn't. The world would look and feel consistent at all levels. But proponents have speculated. Perhaps there are subtle clues. For instance, maybe our physics has clues of quantization or gridding that reflect an underlying computational nature, like the pixelation of a screen. They point to the Planck scale, the smallest unit of length, 1.6 e 35 meters, as possibly the resolution of the universe, or the speed of light as possibly the clock speed of the simulation. These are playful analogies. Mainstream physics considers these just natural limits, not evidence of coding. Another idea: maybe there are anomalies or glitches in our universe that would reveal artificiality. So far, we haven't found any that can't be explained by known or hypothetical natural phenomena. What about our own technology? We already simulate basic universes on computers, virtual environments, video games, even simplified models of physics and cosmology. These are crude compared to reality, but they're improving. It's conceivable that in a few centuries, or millennia, if progress continues, our descendants might simulate conscious minds or entire worlds. Perhaps they'd do it to see their history play out, or just for entertainment, or as research, like running many universes with slightly different constants to see which forms life. If that's feasible, the number of simulated experiences could vastly outnumber original ones, lending weight to the simulation argument from another angle. Now, emotionally, how does this idea sit with us? The thought that everything around us, Earth, the solar system, the stars, the people we love, even our own bodies and thoughts, could be artificial constructions in some cosmic computer. It can be disorienting. Some people find it thrilling, a kind of ultimate conspiracy mystery to solve. Others find it depressing or scary, as if it cheapens reality or puts us at the mercy of unknown creators. But let's step back and consider, if this world is a simulation, we have still known no other reality. This is the world in which we love, strive, create, and wonder. In a very important sense, it is real to us. If you cut your finger, you feel pain. Simulated pain is still pain. If you achieve something great, you feel pride. Simulated pride is still pride. Our emotions and experiences would not be less meaningful. After all, even if we're programs, we are programs capable of feeling and thinking, so those feelings and thoughts matter to us. Furthermore, perhaps being a simulation could be seen in a positive light. It might imply that there is a creator or creators who set this all up. One could hope that such creators have some benevolent intent, or at least an interest in the simulation's outcomes. Perhaps they intervene subtly. Would that be what some people interpret as divine intervention? Or perhaps they just watch. In a way, it's a scientific twist on the idea of a god or gods watching over us. Alternatively, maybe the simulation runs autonomously and the creators are entirely hands-off. In that case, the situation is not much different from a traditional atheist's view of a real universe with no guiding hand. We'd just have an impersonal computer instead of impersonal nature at the bottom of reality. Could we ever contact or communicate with the simulators? That idea veers deep into speculation. Some have half-jokingly suggested that if we made a very obvious attempt to communicate out of the bounds of our universe, say, by arranging bits in a certain pattern, a simulator might notice and respond. Others think if we ever simulate universes ourselves, we might find clues by analogy for our own existence. But these are, at this point, musings in the realm of imagination. It's possible we will never know for sure if we are in a simulation, and maybe it doesn't matter. What matters is how we live our lives and how we treat each other and the world, simulated or not. If you knew 100% that we were in a simulation, what would change for you? Perhaps you might feel a bit more daring, or conversely, a bit more nihilistic, depending on your personality. But the sunrise would still be beautiful. The taste of your favorite meal would still delight you, and the voices of those you care about would still bring you comfort. Life would go on. Maybe one takeaway from the simulation idea is to not take things for granted, to stay curious. Reality might be far stranger than it seems on the surface, so keeping an open mind is healthy. But it also teaches us to cherish the immediate reality we have. Whether base or virtual, this is the arena in which our joys and sorrows play out. Now, with this final cosmic mystery contemplated, we have truly traversed an astonishing range of ideas. We sought the ultimate physical truth in a theory of everything. We entertained extra dimensions hidden in plain sight. We balanced on the razor's edge of a fine-tuned universe, and then expanded outward to a multiverse of countless universes. We fast-forwarded to the death of time, and then questioned the nature of reality itself. Each of these topics alone could fill volumes, and indeed they fill the minds of researchers and thinkers. Here, we have gently floated through them in a reflective, meditative manner, just getting a sense of their scope and significance, letting them enrich our sense of wonder without overwhelming us. And so, our journey draws to a close. We have sailed on the currents of deep time and wandered among cosmic wonders. We sought unity in the laws of nature, stepped beyond the visible dimensions, marveled at a universe finely tuned for life, and imagined realms beyond our own. We peered into the distant future to see how everything might end, and we questioned the very nature of reality. These are immense ideas, almost too vast to hold all at once. Yet we explored them gently, one by one, like stepping stones across a wide river. As we come back to where we began, we find ourselves here, in this present moment, perhaps lying in the dark, listening to these words, breathing quietly. The universe around us is still the same wondrous place that we started with. The stars outside, whether you see them through a window or simply picture them in your mind, still shine with ancient light. We might feel small under that sky, but we can also feel deeply connected. We are made of the same elements that glow in those stars. The laws of physics that govern their burning hearts are the very laws playing out in the cells of our bodies and the synapses of our brains. We are not apart from the cosmos. We are part of it, children of the stars, heirs to billions of years of cosmic evolution, now reflecting on the cosmos that made us. There is a deep peace in acknowledging both our smallness and our unity with the universe. On one hand, the cosmos is vast beyond comprehension, and our lives are tiny flickers. On the other hand, because we are made of this universe and have minds that can appreciate it, the universe lives within us as well. In a way, when we marvel at the cosmos, it is the cosmos marveling at itself through us. And that perhaps is a profoundly meaningful thing. Now, the hour is late and our voyage is ending. Allow your mind to settle like a ship coming to port after a long sail. We've travelled so far in our thoughts, and it's okay to let them gradually come to rest. The grand ideas we encountered can drift into the background, like distant stars, gently fading as sleep draws near. You might find that some ideas, a particular image of a galaxy, or the notion of a multiverse, or just the feeling of the vast ocean of time, gently lingers with you. Let it be a friendly presence. And anything that felt too heavy or complex, you can let go of for now, like releasing a puff of air. Feel the weight of your body against your bed or chair, the pull of gravity that anchors you, the same gravity that shapes planets and keeps the moon in its orbit. It's the universe's gentle way of holding you. Feel the coolness or warmth of the air on your skin, air that has circulated from distant lands, that carries a bit of the world to you as you breathe. Here you are, in this little pocket of space and time, safe and sound, experiencing this very moment. Take a slow, deep breath, filling your lungs, and then exhale softly. With each breath, imagine drawing in peace and spaciousness, and breathing out any tension or residual excitement from our cosmic journey. In and out. The rhythm of your breath is like the gentle ebb and flow of a cosmic tide. As you lie here, imagine for a moment that our journey's ship has gently anchored in a calm, twilight bay. Above, the sky is dark, but sprinkled with stars. The big questions and vistas we explored shine faintly in your memory, like those stars, present, but not demanding your attention, simply twinkling. You are back to the gentle here and now, carrying a treasure of perspective within you. In this moment, there is nothing you need to do, nothing you need to solve or figure out. The universe, in all its vastness, can take care of itself for the night. You can simply be a traveller at rest, a part of all that is, perfectly sufficient, just as you are. The mysteries will be there tomorrow, and the next day, and the next, for whenever you want to ponder them again. For now, you have earned your rest. Our exploration of deep time and cosmic mystery comes to a soft and reassuring end. We set out to sail the currents of cosmic time, and we return with a heart full of wonder and a mind at peace. The night is quiet around you. Perhaps you can hear the faintest sounds in the darkness, your own breathing, the whisper of a breeze, the quiet hum of life continuing softly in the distance. It's the soundtrack of now, the gentle music of a world where everything is okay. Think of all the people out there under this same night sky, many of whom might be sleeping or dreaming at this very moment. We are together in this, on our small planet adrift in space, each of us with our hopes and curiosities. In a way, when you close your eyes, you join that collective dream of humanity and life, all part of the universe's story. You are not alone. You are an irreplaceable note in the symphony of existence. I invite you, if you haven't already, to close your eyes and let the images behind your eyelids form and shift without intention. Maybe you see waves of colour or patterns. Maybe you envision gently drifting through space, not as a cold void, but as a peaceful, velvety expanse. Perhaps you imagine yourself floating, supported, as if the universe itself cradles you. There is no wrong way to feel. If you are very alert still, that's okay. Just continue to breathe slowly and feel the calm. If you are already drowsy, let that drowsiness deepen. As our journey ends, a gentle contentment washes over us. We have touched the edges of knowledge and wonder, and now we come home to ourselves. In this quiet conclusion, feel the simple joy of being alive, here, now. Feel gratitude, perhaps. Gratitude to the cosmos for existing, to the earth for supporting us, to the long chain of events that led to you being here, and even gratitude to yourself for taking this time to journey and now to rest. Thank you for travelling with me through these vast realms of time and thought. In the great cosmic scale, our time here has been a mere blink, yet it feels rich and full. I hope this voyage has brought you some insight, some peace, and a sense of connection to the universe and to the quiet strength within you. The night is yours now. Let the quiet of the cosmic night wrap around you like a warm, dark blanket sprinkled with starlight. You might imagine those far-off stars gently watching over you, like friendly guardians twinkling in the distance, each one a sun that says, "Sleep, child of the universe. We will keep the darkness beautiful for you." Now let yourself drift. Drift like a boat on calm waters, like a planet in its tranquil orbit, like a thought turning into a dream. There is nothing to fear in this vastness. It is the same place that gave you life and to which you belong. Sink into the comfort of your bed. Every muscle can relax now, letting go of any remaining tension. Your toes relax, your legs, your abdomen and chest, your shoulders, your arms and hands, your neck, your face. If you notice any tightness, breathe into it and release. Gravity is your friend, pulling you gently down into rest. Feel the ease of this surrender to the night. Your mind, having been so active and curious, can take a gentle bow and step back. The thinking part of you can rest, knowing it has done well. If stray thoughts come, acknowledge them and let them pass, like clouds across the sky. There is a soft darkness behind your closed eyes, and within that darkness, perhaps, the seeds of dreams. Maybe your dreams will carry echoes of our journey. Perhaps you'll find yourself flying among galaxies, or meeting wise beings, or simply enjoying a heightened awareness within a fantastical reality. Or maybe your dreams will be of something entirely different and personal. Whatever comes, let it come. You are safe here, in the haven of your sleep. We end our tale in a gentle whisper, tapering off into the same silence from which we began. Remember, you are a part of this universe, and it is a part of you. That connection is unbreakable and serene. Sleep now, and as you do, may you feel the quiet thrill of knowing that even in slumber, you are sailing through space on this earth, and the atoms in your body are dancing to the tune of cosmic rhythms. May your rest be as deep and calm as the space between the stars. Sleep well under the infinite sky. Good night.